Hello there, and welcome to Umber Dreams Archives. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable wherever you are. Let your body settle into this moment. Where in the world are you watching from? A quiet bedroom where the day has finally ended. A cozy space where you can let your thoughts slow down and drift. Tonight we're going to explore one of the most profound moments in Earth's history. The final hours before the extinction of the dinosaurs. 66 million years ago. We'll discover what that last ordinary day was like, understand the science of what happened when a mountain from space struck our planet, and contemplate what it means that an entire world could end in an afternoon. It's a journey that spans deep time, touches the very edge of planetary catastrophe, and ultimately reveals something beautiful about survival and change. But don't worry. This isn't going to be a disaster film or a scary countdown to destruction. Instead, we'll move slowly and carefully through the science, the evidence, and the story, taking our time with each discovery. We'll explore the world as it was, understand the physics of what happened, and by the end, I think you'll find something peaceful in how life persevered. This is a story about endings, yes, but also about beginnings, and about how fragile and persistent life can be at the same time. If you enjoy these calm explorations of deep time and cosmic events, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these quiet journeys through time. So settle in now, let your shoulders drop away from your ears, take a slow breath, and then another. And let's begin our slow drift back through 66 million years to a world that vanished in fire and darkness, and to the life that somehow found a way forward. There's nowhere you need to be right now, nothing you need to do. Just listen and let the story unfold at its own gentle pace. Let's begin by imagining an ordinary morning 66 million years ago. The sun rises over what will one day be called the Yucatan Peninsula, but on this morning it's a shallow tropical sea, warm and teeming with life. The water is clear and turquoise, lapping gently against islands covered in ferns and flowering plants. In the forests that stretch across what will become North America, dinosaurs are doing what they've done for 165 million years, living, eating, breathing, existing in a world that feels permanent. There's a triceratops at the edge of a river, dipping its massive head to drink. A herd of Edmontosaurus moves through the underbrush, making the small sounds of family groups, the young ones staying close to their mothers. Somewhere in the distance, a Tyrannosaurus calls out, a sound that has echoed through these forests for millions of generations. The day is unremarkable. The sky is clear. There is no warning, no sign, nothing to suggest that this is the last normal day this world will ever know. Above the atmosphere, something is approaching. It has been approaching for millions of years, actually, travelling through the darkness of space on a trajectory set long before dinosaurs walked the Earth. It's a piece of rock and metal, roughly 6 miles across, moving at 45,000 miles per hour. If you could see it from the ground, it would look like a new star appearing in the daylight sky, growing brighter with each passing moment. But no one is looking up. The dinosaurs have no concept of space, no understanding of astronomy, no way to know what's coming. They are simply living their last moments in a world that has existed in various forms for hundreds of millions of years. The Cretaceous period has been ongoing for 79 million years. The dinosaurs have dominated terrestrial ecosystems for longer than that. This morning feels like every morning that has come before it. The asteroid, which scientists would later name after the impact crater it creates, is now entering Earth's atmosphere. It's moving so fast that the air in front of it cannot get out of the way quickly enough. The air compresses, heats, begins to glow. The sky itself starts to burn. And this brings us to something we need to understand about the physics of what's about to happen, because the scale of this event is almost impossible to grasp without carefully considering the numbers involved. To understand what happens when a 6-mile wide asteroid strikes Earth at 45,000 miles per hour, we need to think about energy. Not in an abstract way, but in concrete, carefully measured terms that help us comprehend something that exists outside normal human experience. The asteroid carries kinetic energy, the energy of motion. The equation is simple enough: 1/2 times mass times velocity squared. But when we plug in the numbers, the mass of a mountain of rock and metal, the velocity of something moving at cosmic speeds, the result is a number so large it becomes meaningless unless we find comparisons. The energy released in this impact is equivalent to about 100 million megatons of TNT. That's roughly 2 million times more powerful than the most powerful nuclear weapon ever detonated by humans. But even that comparison fails to capture the reality, because nuclear weapons are brief, localized events. This impact releases all that energy in a single moment, yes, but the consequences propagate outward in waves of destruction that eventually encompass the entire planet. Think of it this way: if you were standing in what is now Denver, Colorado, about 1,500 miles from the impact site, you would still experience effects that would be instantly fatal. The energy doesn't dissipate quickly. It transforms, spreading as heat, as shock waves, a seismic energy that shakes the entire Earth. The asteroid itself is not made of anything exotic or strange. It's mostly rock, similar to the material that makes up Earth's crust, with some iron and nickel mixed in. Scientists have analysed the layer of debris left behind by the impact and found elevated levels of iridium, an element that's rare in Earth's crust but common in asteroids. This chemical signature, discovered in 1979 by Luis and Walter Alvarez and their colleagues, was the first strong evidence that an asteroid impact had caused the mass extinction. The iridium layer appears in rock formations all over the world, a thin band of extraterrestrial dust marking the exact moment when one world ended and another began. What's remarkable is how ordinary the asteroid is in cosmic terms. Space is full of objects like this, rocky remnants from the formation of the solar system, orbiting the Sun in the vast region between Mars and Jupiter. Most will never threaten Earth. Their orbits are stable, predictable, safe. But gravitational interactions, collisions with other asteroids, the slow perturbations of Jupiter's massive gravity, all these factors can occasionally knock something out of its orbit and send it on a new path. The asteroid that hit Earth 66 million years ago was simply unlucky, pulled by gravity into a trajectory that happened to intersect with our planet's orbit at precisely the wrong moment. The odds of such an impact for any given year are extremely low. But over millions of years, over the vast stretches of geological time, unlikely events become inevitable. Earth has been struck many times in its history. We can see the scars, the ancient craters, the disrupted rock layers. Most impacts were smaller, local catastrophes rather than global ones. But every few tens of millions of years, something large enough to change everything arrives from the darkness. And on this particular morning, 66 million years ago, that something is about to make contact with the shallow sea near the Yucatan Peninsula, and the world as it has existed for millions of generations is about to end in fire. Before we watch this world end, let's spend a moment understanding what's about to be lost. The late Cretaceous period, the final chapter of the Age of Dinosaurs, is a world of remarkable biodiversity and complexity. It's not the simplistic primordial landscape we sometimes imagine. It's a sophisticated ecosystem, the product of hundreds of millions of years of evolution, as complex in its way as the world we inhabit today. The dinosaurs themselves represent an astonishing variety of forms and lifestyles. There are the massive sauropods, though they're less common now than they were in the Jurassic period. There are the ceratopsians like Triceratops, with their elaborate horns and frills, living in herds that move across the landscape like the bison that will one day roam these same plains. There are the hadrosaurs, the duck-billed dinosaurs, some of which have elaborate crests that they use to make sounds, to call to each other across the valleys and forests. And there are the predators. The tyrannosaurs and smaller raptors, filling every ecological niche from apex predator to small bird-like hunters. But the dinosaurs are not alone. The skies are filled with pterosaurs, flying reptiles that have evolved to extraordinary sizes. Quetzalcoatlus, one of the largest, has a wingspan of 36 feet, making it the largest flying creature that has ever existed on Earth. When one passes overhead, it must cast a shadow like a small airplane. In the oceans, mosasaurs patrol the depths, marine reptiles that have evolved from land-dwelling ancestors to become the dominant predators of the Cretaceous seas. Some grow to 50 feet in length, with powerful jaws lined with teeth designed to crush the shells of giant ammonites. The plants, too, are different from anything we know today, but also strangely familiar. Flowering plants, angiosperms, have recently evolved and are spreading rapidly across the continents. There are recognizable trees, magnolias and sycamores, alongside ferns and cycads and conifers that have been present since before the dinosaurs evolved. The forests are dense, productive, filled with the sound of insects and the calls of small, primitive mammals that live in the undergrowth, waiting for the opportunity that extinction will soon provide. And all of this complexity and diversity and ancient success, all of it is about to end. Not slowly. Not through gradual climate change or sea level rise or competition with better adapted species. It will end in a single afternoon, in fire and darkness, because of a piece of rock that happens to be in the wrong place at the wrong time. And that brings us to the moment itself, to the impact, to the instant when everything changes forever. The asteroid enters the atmosphere travelling faster than anything that has ever moved through Earth's air. At this speed, the normal rules of atmospheric entry don't quite apply. There's no gradual heating, no controlled descent. The object is simply too large and moving too fast for the atmosphere to slow it down in any meaningful way. As it descends, the air in front of the asteroid compresses to incredible densities and temperatures. The air itself begins to glow, then to plasmaize, stripping electrons from atoms and creating a tube of superheated, ionized gas thousands of degrees hot. This plasma trail is visible for thousands of miles in every direction, a new sun appearing in the sky, growing brighter and larger with each fraction of a second. The sonic boom, when it comes, is not like the crack of a supersonic jet. It's a sustained roar, a wall of sound that precedes the asteroid, compressing the air into a shockwave that rattles the ground and causes trees to sway even hundreds of miles away from the impact point. Animals look up, startled by this unprecedented sound, by the bright light in the sky, by the sudden, inexplicable wrongness in the air. But there's no time to flee, no time to seek shelter, no time for anything except to witness the final moments of the world they know. The asteroid strikes the shallow sea at an angle, not perpendicular to the surface but coming in at perhaps 20 to 30 degrees from horizontal. This angle, which scientists have calculated from the shape of the crater and the distribution of debris, actually makes things worse. A vertical impact would have sent more material straight up and out into space. The angled impact directs more energy horizontally, across the surface, spreading destruction more efficiently across the planet. The moment of contact lasts less than a second, but in that fraction of time the entire asteroid punches through the shallow water, through the several hundred feet of sedimentary rock beneath, and into the bedrock below. The energy released is so enormous that it vaporizes the asteroid itself, along with thousands of cubic miles of rock. There's no impact crater in the traditional sense, not at first. There's a growing sphere of superheated vapor and plasma, expanding outward at supersonic speeds, obliterating everything it touches. The rock beneath the impact point behaves like a liquid under this much pressure. It flows, splashes upward in massive jets, rebounds from the center like a drop of water filmed in slow motion but on a scale of miles. The crater forms rapidly, deepening and widening, surrounded by a rim of shattered, uplifted rock. Within seconds, the crater is 12 miles deep and more than 100 miles across, though it will eventually collapse and settle into a final form about 93 miles in diameter and 12 miles deep in the centre. The energy of the impact liquefies rock for miles in every direction. Massive volumes of molten material are ejected straight up, some of it reaching orbital velocity and escaping Earth's gravity entirely, eventually falling back as a rain of molten glass and stone. Most falls back within hours, starting countless fires as it re-enters the atmosphere. The heat is so intense that the very air catches fire, creating a thermal pulse that can cause spontaneous combustion hundreds of miles from the impact site, and we're still in the first few seconds. The actual destruction is only beginning. The shockwave, travelling through solid rock faster than the speed of sound in air, has already begun its journey around the planet. The thermal radiation, the flash of heat and light from the vaporized rock and asteroid, is propagating outward at the speed of light. And the material ejected into the upper atmosphere, the pulverized rock and vaporized ocean, is beginning its journey around the world, spreading a layer of debris that will eventually blanket the entire Earth. But let's pause here, at this moment of maximum violence, and consider what happens next. The cascading series of catastrophes that turn a local event into a global extinction. The shockwave travels outward from the impact site at several miles per second through solid rock, much faster than any earthquake, faster than any natural phenomenon except perhaps a volcanic eruption at its most violent. When it reaches the surface, the ground doesn't just shake, it jumps, ripples, flows like water. Trees are uprooted instantly. Rock formations that have stood for millions of years shatter and collapse. Any dinosaur within 500 miles of the impact site dies in seconds, crushed by falling trees, buried in landslides, thrown through the air by the heaving ground. The shockwave propagates through the Earth's crust and mantle, weakening as it spreads but still powerful enough to trigger earthquakes on the opposite side of the planet. In what will one day be India, there are massive volcanic fields, the Deccan Traps, which have been erupting for hundreds of thousands of years. The seismic energy from the impact may intensify these eruptions, though scientists still debate the extent of this effect. What's clear is that the impact adds seismic stress to a planet already in a state of geological flux. Above ground, the thermal pulse arrives at the speed of light. Imagine standing 1,000 miles from the impact. The sky suddenly becomes brighter than the sun, bright enough to cause instant blindness if you look directly at it. The air temperature spikes, rising dozens of degrees in seconds. Anything flammable near enough to the impact, dry vegetation, forests, even living tissue in some cases, begins to smoulder and then ignite. The heat is brief but intense, a flash of infrared radiation that passes in moments but leaves behind countless fires. The ejected material, rock and water vaporized by the impact, begins to fall back to Earth. The larger pieces, boulders and chunks of molten rock the size of houses, fall first, creating secondary craters, adding more destruction to an already devastated landscape. Then comes the rain of smaller debris, pebbles and fragments and droplets of molten glass called tektites. This material is hot enough to ignite whatever it touches. Forests that survived the initial thermal pulse now catch fire from above as a literal rain of fire descends from the sky. The fires spread rapidly, consuming the forests of North America first, then spreading to other continents as the ejected material falls around the globe. Some scientists estimate that as much as 70% of Earth's forests burn in the hours and days following the impact. The smoke from these fires rises into the stratosphere, adding to the veil of dust and debris already beginning to encircle the planet. The sky, everywhere on Earth, begins to darken as this material spreads. In the ocean near the impact site, the water hasn't just been vaporized. It's been displaced on an unimaginable scale. The impact creates a cavity in the ocean hundreds of feet deep and hundreds of miles across. Water rushes in to fill this void, creating the mother of all tsunamis. The wave that forms is not like the tsunamis we know today, and through all of this, the world is changing in ways that won't be fully apparent for hours or days. The dust and debris in the atmosphere is beginning to circle the globe, carried by high-altitude winds. The sun, which has shone on Earth for billions of years, is starting to dim as this material blocks and scatters its light. And this is where the true, long-term catastrophe begins, not in the immediate violence of the impact, but in the slow starvation of light that will bring darkness to a planet that depends on the sun for almost everything. And it's this darkness, this failure of photosynthesis, that will ultimately determine which species survive and which vanish forever. Within hours of the impact, the nature of the catastrophe shifts from immediate violence to something more insidious and far-reaching. The fires are still burning across multiple continents. The tsunamis are still washing back and forth across ocean basins. But the planet's atmosphere is undergoing a transformation that will prove more deadly than either of these direct effects. The dust and pulverized rock ejected by the impact, along with the soot from the global wildfires, is accumulating in the stratosphere. This isn't weather in the normal sense. Weather happens in the troposphere, the lowest layer of atmosphere, where rain can wash particles out of the air. But the material from the impact has been thrown much higher, into the stratosphere, where there is no rain, no mechanism to bring it down quickly. It will remain suspended there for months, perhaps years, circling the globe on the high-altitude winds. The effect on sunlight is immediate and profound. Within hours, the light reaching Earth's surface begins to dim perceptibly. By the end of the first day, the sky everywhere on Earth has taken on a strange twilight quality. The sun, when visible at all, appears as a dim red disk through the haze. The light level is dropping towards something like a moonlit night, even at noon, and this is just the beginning. Photosynthesis, the process by which plants convert sunlight into chemical energy, requires a certain minimum light level to function. Different plants have different thresholds, but as the light continues to dim over the following days and weeks, more and more plants reach their compensation point, the level where they're consuming more energy than they're producing. Growth stops first, then maintenance of existing tissue becomes impossible, and finally the plants begin to die. In the oceans, the effect is even more immediate. Phytoplankton, the microscopic organisms that form the base of the marine food chain, are among the most light-dependent organisms on Earth. They live in the upper layer of the ocean, where sunlight can penetrate, and they need bright light to photosynthesize efficiently. As the sky darkens, phytoplankton populations crash within weeks. The zooplankton that feed on them soon follow, then the small fish, then the larger fish, then the marine reptiles at the top of the food chain. On land, the herbivorous dinosaurs are faced with a gradually worsening food crisis. The plants they depend on are dying, and there's nothing they can do about it. A triceratops needs to eat hundreds of pounds of vegetation every day to maintain its body mass. As the plants wither and die, these massive animals begin to starve. They might browse on dead vegetation for a while, on the dried remains of forests, but without fresh growth, without the nutrients that come from living plants, they're living on borrowed time. The carnivores, paradoxically, might have a brief period of abundance. There are dying herbivores everywhere, easy prey even for predators that are themselves weakened by hunger. But this abundance is an illusion, a temporary spike before the crash. Once the herbivores are gone, the carnivores will have nothing to eat. A Tyrannosaurus, requiring perhaps several hundred pounds of meat per week, cannot survive long without prey. And unlike some smaller animals, it cannot simply hibernate and wait for better conditions. The temperature is also beginning to drop. Without sunlight warming the surface, the planet is losing heat to space faster than it's being replaced. The warm, equable climate of the late Cretaceous is beginning to break down. The first frosts appear in regions that have been frost-free for millions of years. Cold-blooded animals, which depend on external heat sources to maintain their body temperature, are particularly vulnerable. The larger dinosaurs might retain heat better due to their size, but even they cannot survive indefinitely without sunlight to warm them. The darkness is not absolute. There's still some light, enough to see by, roughly equivalent to deep twilight or a heavily overcast day. But it's not enough for plants, not enough for the complex ecosystems of the Cretaceous to function, and it will persist, this twilight world, for months at minimum, possibly years in some estimates. The world has become a cold, dark, dying place, and for most of the species that inhabited it just days before, there is no adaptation, no behaviour change, no refuge that can save them. And that brings us to consider who survives this catastrophe and why. Because understanding survival is as important as understanding extinction. Not everything dies in the impact winter. If it did, there would be no story to tell, no life to eventually evolve into the forests and oceans we know today. Understanding what survives, and why, reveals important patterns about how life persists through catastrophes. Size matters enormously, but not in the way you might expect. The very largest animals, the dinosaurs that weigh several tons, are among the most vulnerable. They require massive amounts of food to maintain their metabolism, food that simply isn't available in the dark, cold world after the impact. There's no mechanism by which a 10-ton Edmontosaurus can reduce its food requirements enough to survive months or years of ecosystem collapse. It needs thousands of calories every day, and those calories are no longer available. But very small animals have options that large ones don't. A mammal weighing just a few pounds can hibernate, slowing its metabolism to a fraction of normal, surviving for months on stored body fat. It can eat seeds, nuts, the preserved energy from plants that grew before the impact. It can shelter underground, insulated from the temperature swings, protected from the worst of the environmental chaos above. Small size in this catastrophe is an enormous advantage. The survivors, as the fossil record shows, follow predictable patterns. Small mammals survive in relatively large numbers. They're omnivorous, adaptable, capable of eating almost anything organic. In the desperate months after the impact, this might mean eating dead vegetation, insects, carrion, seeds, whatever provides calories. Their small size means they can survive in microhabitats, small pockets of relative stability in an otherwise devastated landscape. Birds survive, though many species go extinct. The survivors are generally the smaller, more generalized species, ones that can eat seeds and insects, that can nest in protected locations, that don't depend on large, stable territories. The more specialized birds, particularly the larger ones, mostly vanish, but enough survive to repopulate the world, to eventually diversify into the astonishing variety of birds we see today. Crocodilians survive remarkably well. These are the archosaurs, the group that includes both crocodiles and dinosaurs, but unlike their dinosaur cousins, crocodiles make it through the extinction with only moderate losses. The reason probably relates to their lifestyle. Crocodiles can go months without eating. They're cold-blooded, so they don't need to maintain a constant body temperature. They live in aquatic environments, which might provide some buffering from temperature extremes. And they're generalist predators, capable of eating almost anything they can catch, from fish to dead animals washed into the water. Plant seeds survive in large numbers. A seed is a remarkable structure, a plant embryo surrounded by stored food, all protected by a tough outer coat. Seeds can remain dormant for years, waiting for conditions to improve. When sunlight finally returns and temperatures rise, these seeds germinate, and the plants begin to grow again. But the plants that come back first are not the same ones that dominated before. Fast-growing opportunistic species colonize the devastated landscape first, creating an ecology very different from the complex forests of the late Cretaceous. There's an element of chance in all of this, of course. Some species survive because they happen to be in the right place at the right time, sheltered from the worst effects by geography or luck. Some survive because they have traits that were evolved for entirely different purposes, but happen to be useful in this catastrophe. The mammal's small size, for instance, evolved in a world dominated by dinosaurs, where staying small and nocturnal and unobtrusive was a survival strategy. But that same small size becomes crucial when the dinosaurs vanish, and size is suddenly a liability rather than an asset. And there's a deeper pattern here, one that appears again and again in the history of life on Earth. Specialists, organisms highly adapted to specific conditions, are vulnerable when those conditions change rapidly. Generalists, organisms that can adapt to various conditions, eat various foods, live in various environments, those organisms tend to survive catastrophes better. The dinosaurs, for all their success, had become specialists in many ways, finely tuned to the world of the late Cretaceous. When that world vanished, they couldn't adapt fast enough, and that brings us to the question of how long this darkness persisted and what the world looked like when light finally returned. The immediate aftermath of the impact, the fires and tsunamis and shockwaves, last for hours or days. But the real catastrophe, the impact winter, persists for months at minimum, possibly years. This is time measured not in human terms but in the slow starvation of ecosystems. The gradual depletion of stored energy, the waiting for light that may never return. Imagine the world 3 months after the impact. The fires have mostly burned out, having consumed much of what was combustible. The ash and dust in the atmosphere have settled somewhat, but enough remains to keep the sky perpetually dark. The temperature has dropped significantly, perhaps 20 or 30 degrees Celsius globally. Enough to bring freezing conditions to regions that have been tropical for millions of years. The oceans, which store heat better than land, are cooling more slowly, but even they are beginning to chill. The survivors are living in a world of scarcity. The herbivores that remain are desperately browsing on whatever plant material still exists, stripping bark from dead trees, eating dried leaves, digging for roots. But there's only so much of this stored energy available. And it's not being replaced. Every day, more herbivores die. Their bodies provide temporary food for the carnivores and scavengers, but this too is a finite resource, drawing down the stored energy of the ecosystem without replenishment. The mammals, small and hidden, are faring better. They can find seeds, can eat insects that themselves are feeding on dead organic matter, can scavenge on the endless supply of dead dinosaurs. In some ways, these months are a bonanza for opportunistic feeders. There's more dead biomass than they could possibly consume. But they're also facing the cold, the darkness, the general hostility of the environment. Many die, but enough survive in protected burrows, in caves, in any shelter they can find. In the oceans, the die-off is catastrophic. Without phytoplankton, the entire food chain collapses from the bottom up. The ocean floor is covered with a layer of dead organisms, marine snow falling continuously from above as entire ecosystems die. This layer will eventually fossilize, becoming part of the geological record, a clear marker of the extinction event. But in the moment, it's simply death on an incomprehensible scale, the largest mass mortality event in Earth's oceans in tens of millions of years. Some aquatic environments might provide refuges. Deep ocean vents, where life doesn't depend on photosynthesis but on chemical energy from the Earth itself, continue functioning. These chemosynthetic ecosystems, powered by volcanic heat rather than sunlight, are unaffected by the darkness above. They're small, isolated, representing a tiny fraction of ocean life, but they demonstrate that not all ecosystems depend on the sun. Freshwater environments might also serve as refuges. Lakes and rivers, particularly those fed by glaciers or groundwater, might maintain some level of productivity even in the darkness. Nutrients washing in from the dead terrestrial ecosystems could actually stimulate growth of algae and bacteria, creating small, temporary oases of life in an otherwise dead world. Animals that can access these environments have a better chance of survival. The darkness begins to lift, gradually, after several months. The largest particles fall out of the atmosphere first, pulled down by gravity. Rain, when it starts again, helps wash smaller particles out of the air. Slowly, incrementally, the light level begins to rise. The sun becomes visible again, first as a dim disk, then brighter, and finally approaching its normal intensity. But the world it illuminates is profoundly different from the one that existed before. The first plants to grow back are fast-growing opportunists, ferns and mosses, and simple flowering plants that can colonize disturbed ground quickly. They spread across a landscape that's been scoured by fire and erosion, creating a green carpet where forests once stood. These early successional species don't create the complex ecosystems of the Cretaceous, but they do begin the process of photosynthesis again, converting sunlight back into chemical energy, rebuilding the base of the food chain. As plant productivity resumes, the surviving herbivores, mostly small mammals and some reptiles, begin to recover. With food available again, populations stabilize and then start to grow. The pressure of starvation eases. The world remains impoverished, simplified, lacking the diversity and complexity it once had, but it's alive, functioning, capable of supporting life. But the dinosaurs, with very few exceptions, are gone. Some might persist for a time in isolated refuges, small populations clinging to existence in places where conditions are slightly better. There are tantalizing hints in the fossil record of dinosaurs that might have survived for thousands of years after the impact. But these are brief postponements, not true survival. The world has changed too much, become too cold, too seasonal, too unstable for animals that evolved in the stable, warm world of the Mesozoic. And this brings us to the question of what the fossil record actually shows us about this event, and how scientists piece together this story from fragments of rock and bone. The story of the asteroid impact is written in stone, quite literally, in layers of rock that accumulated in the days and months and years following the event. Understanding this story requires careful reading of these rocks, interpreting the clues they contain, piecing together a narrative from evidence that is fragmentary, scattered across the globe, sometimes contradictory. The most obvious evidence is the iridium layer, discovered in 1979 by Luis Alvarez, a physicist, and his son Walter, a geologist. They were studying a thin clay layer in Gubbio, Italy, a layer that marked the boundary between the Cretaceous and Paleogene periods. Chemical analysis showed this layer contained unusually high concentrations of iridium, an element that's rare in Earth's crust but relatively common in meteorites and asteroids. This discovery was revolutionary because it provided a testable hypothesis. If an asteroid had hit Earth 66 million years ago, then the iridium layer should be global, present everywhere at the same geological level. And that's exactly what subsequent research found. The iridium anomaly appears in rock formations on every continent, in marine sediments and terrestrial deposits, always at the Cretaceous-Paleogene boundary. The consistency of this evidence is compelling, difficult to explain by any mechanism other than an extraterrestrial impact. But the iridium layer is just one piece of evidence. The rocks also contain shocked quartz. Mineral grains that have been subjected to pressures so extreme that their crystal structure is deformed in characteristic ways. Shocked quartz forms during meteorite impacts or nuclear explosions, situations where rock is subjected to momentary pressures of millions of pounds per square inch. The presence of shocked quartz at the Cretaceous-Paleogene boundary, scattered globally, supports the impact hypothesis. Then there's the soot layer, evidence of the massive wildfires that followed the impact. In some locations, particularly in North America, the boundary layer contains so much soot that it's visibly black. Analysis of this soot shows it came from burning vegetation, specifically from forest fires that consumed enormous areas. The amount of soot suggests that a significant percentage of Earth's forests burned, consistent with the fire from above scenario suggested by computer models of the impact. The tektites, small glass beads formed when molten rock is ejected into the air and cools rapidly, appear in the boundary layer throughout the Caribbean region and in other locations around the world. These provide direct physical evidence of material thrown up by the impact, rock that was melted, ejected, and frozen into glass as it cooled during flight. The chemistry of these tektites matches the rock at the Chicxulub crater site, linking them definitively to that specific impact. The crater itself, Chicxulub, buried beneath younger sediments on the Yucatan Peninsula, was identified in the early 1990s through gravitational and magnetic surveys. The crater is huge, roughly 93 miles in diameter, one of the largest impact structures on Earth. Drilling into the crater has recovered shocked rock, melted material, and other direct evidence of the impact. The age of the crater, determined through radioactive dating, matches the age of the Cretaceous-Paleogene boundary precisely, 66 million years ago. But perhaps the most dramatic evidence is the fossil record itself. In rock layers just below the iridium layer, dinosaur fossils are abundant. In layers just above, they're absent. The transition is sharp, geologically instantaneous. One moment, in geological terms, dinosaurs are everywhere. The next, they're gone. Along with them vanish the pterosaurs, the mosasaurs, the ammonites, and many other groups. The extinction is clear, undeniable, one of the 5 largest mass extinctions in Earth's history. The scientific debate now is not about whether the impact happened or whether it caused the extinction. The evidence for both is overwhelming. The debates are more subtle, about the exact sequence of events, the relative importance of different killing mechanisms, the role of other factors like volcanic activity or sea level change. Some scientists argue that the Deccan Traps eruptions in India, which were ongoing at the time, might have stressed ecosystems and made them more vulnerable to the impact. Others suggest that the impact alone was sufficient to cause the extinction. These are the kinds of refinements that science makes, working to understand not just what happened, but how it happened, in what order, with what relative effects. The broad outlines are clear. An asteroid struck Earth 66 million years ago, releasing energy equivalent to billions of atomic bombs, triggering global wildfires, ejecting enough dust to darken the sky for months, causing a mass extinction that eliminated about 75% of all species on Earth. The details, the specific mechanisms, the exact timeline, these are still being worked out, refined with each new discovery, each new technique, each new line of evidence. And this pursuit of understanding brings us to consider how scientists do this work, how they take fragmentary evidence and build from it a coherent narrative of events that happened millions of years before humans existed. The story of how we know about the asteroid impact is itself a remarkable tale of scientific detective work, collaboration across disciplines, and the gradual accumulation of evidence that eventually becomes undeniable. It begins, as many scientific stories do, with curiosity about something that didn't quite make sense. Luis Alvarez was a physicist, a Nobel laureate who had worked on the Manhattan Project and made fundamental contributions to particle physics. His son Walter was a geologist studying the rocks in Italy. They were both puzzled by that thin clay layer in Gubbio, the one that marked the boundary between the age of dinosaurs and the age of mammals. What caused this layer? Why was it there? What did it represent in terms of time? They decided to measure the iridium content of the clay, thinking it might give them a way to determine how long it took to deposit. Their reasoning was that iridium falls to Earth constantly in cosmic dust from space, at a slow but steady rate. If they knew the iridium concentration and the background accumulation rate, they could calculate the time represented by the clay layer. It was a clever approach, indirect but potentially informative. What they found instead was a concentration of iridium far higher than could be explained by normal cosmic dust accumulation. The only way to get that much iridium concentrated in such a thin layer was to have a large iridium-rich object, like an asteroid, hit Earth and spread material globally. This was not what they were looking for, but it was impossible to ignore. The paper they published in 1980 in the journal Science proposed the impact hypothesis and predicted that the iridium layer should be found worldwide. This was a testable prediction, the hallmark of good science. And over the next few years, teams working in different countries found exactly that. The iridium layer appeared everywhere, always at the Cretaceous-Paleogene boundary, always with similar concentrations. The evidence accumulated rapidly. But where was the crater? An impact large enough to cause global effects should leave a huge crater, tens of miles across, and no such crater was known. Critics pointed to this as a weakness in the hypothesis. Perhaps the iridium came from massive volcanic eruptions instead, they suggested. Perhaps it was something other than an asteroid. The crater was found through a combination of old data and new thinking. In the 1950s, oil exploration companies had done gravitational and magnetic surveys over the Yucatan Peninsula, looking for geological features that might indicate oil deposits. These surveys had revealed a huge circular structure buried beneath the sediment, but at the time, no one understood what it was. The data sat in archives, mostly forgotten. In 1990, Alan Hildebrand, a graduate student at the time, and several colleagues began looking at this old data with new eyes. They realized the circular structure matched what you'd expect from a huge impact crater, and its location in the Caribbean made sense given the distribution of tektites and other impact debris. But proving it was the crater required drilling, collecting samples, dating the rocks. The drilling campaigns of the early 1990s recovered shocked quartz, melted rock, and other definitive evidence of impact. Radioactive dating of these materials gave an age of 66 million years, exactly matching the Cretaceous-Paleogene boundary. The crater, named Chicxulub after a nearby town, was confirmed as the impact site. The final major piece of the puzzle was in place. Since then, research has continued, refining our understanding of the impact and its effects. Computer models have simulated the impact itself, the ejection of material, the propagation of the shockwave, the trajectory of debris. These models have become increasingly sophisticated, incorporating better physics, more computational power, more detailed understanding of atmospheric processes. They show us what we could never observe directly: the moment of impact, the explosion, the firestorm, the darkness that followed. Fieldwork continues too. Scientists study rock formations around the world, looking for evidence of the impact's effects. They examine fossil beds, looking for patterns in which species survived and which went extinct. They analyze the chemistry of rocks and fossils, looking for clues about temperature, atmosphere composition, ocean chemistry in the aftermath of the impact. Each study adds detail, context, depth to our understanding. And there's something beautiful about this process, this gradual assembly of truth from fragments. No single piece of evidence proves the impact hypothesis. It's the accumulation of evidence from multiple sources, multiple methods, multiple lines of inquiry, all pointing to the same conclusion. The iridium layer suggests an asteroid. The shocked quartz confirms extreme pressures. The soot layer shows global fires. The crater provides the smoking gun. The fossil record shows the extinction. Together, these form a coherent narrative, a story that explains what happened and why. This is how science works at its best, not through sudden revelation or individual genius, though both play a role, but through collaboration, through the sharing of data and ideas, through the building of consensus based on evidence. The story of the Chicxulub impact is a triumph of this process, a demonstration of how careful observation, rigorous analysis, and open-minded thinking can reveal truths about events that happened millions of years before any human walked the Earth. And this brings us to consider what this extinction event means in the larger context of Earth's history, how it compares to other mass extinctions, and what patterns we can discern from these catastrophic events. The extinction of the dinosaurs, dramatic as it was, is not unique in Earth's history. It's one of 5 major mass extinctions that have occurred over the past 500 million years, events when a significant percentage of all species on Earth vanished in geologically brief periods. Understanding these extinctions, comparing them, looking for patterns, helps us see the Chicxulub impact in context and understand the resilience and fragility of life. The earliest of these 5 mass extinctions occurred at the end of the Ordovician period, about 445 million years ago. At this time, most complex life existed in the oceans. The land was still largely barren, colonized by only the most primitive plants and arthropods. The extinction eliminated about 85% of all marine species, making it one of the deadliest events in Earth's history. The cause appears to have been climate change, specifically a rapid glaciation followed by equally rapid warming, changes that disrupted ocean circulation and chemistry. The second major extinction happened at the end of the Devonian period, about 375 million years ago. This one unfolded more slowly than the others, over several million years, but it was devastating nonetheless, particularly for marine life. Coral reefs collapsed. Fish species vanished. The causes are still debated, but likely involve a combination of climate change, ocean anoxia, where parts of the ocean lost oxygen, and possibly asteroid impacts, though nothing on the scale of Chicxulub. The third and most devastating extinction of all occurred at the end of the Permian period, about 252 million years ago. This one, often called the Great Dying, eliminated about 96% of all marine species and 70% of terrestrial vertebrate species. It was the closest life on Earth has come to complete annihilation. The causes involved massive volcanic eruptions in Siberia, the Siberian traps, which released enormous amounts of carbon dioxide and other gases, triggering extreme global warming, ocean acidification, and widespread anoxia. Life barely survived. It took millions of years for ecosystems to recover and diversify again. The fourth major extinction happened at the end of the Triassic period, about 201 million years ago. This extinction cleared the way for the dinosaurs to become dominant, eliminating many of the large predators and herbivores that had previously controlled terrestrial ecosystems. The causes likely involve volcanic activity again, the Central Atlantic magmatic province eruptions, which occurred as the supercontinent Pangaea began to break apart, opening the Atlantic Ocean. The resulting climate change and environmental disruption eliminated about 76% of all species. And then, 66 million years ago, came the fifth major extinction, the one we've been exploring, the Cretaceous Paleogene extinction caused by the Chicxulub impact. This one eliminated about 75% of all species, including all non-avian dinosaurs, pterosaurs, marine reptiles, and many other groups. It was unusual among the Big Five because it had a clear, identifiable external cause. Most of the other major extinctions appear to have been caused by internal Earth processes: volcanism, climate change, ocean chemistry changes, rather than external cosmic events. Looking at these 5 extinctions together reveals some patterns. They're all associated with rapid environmental change, rapid in geological terms, meaning thousands or tens of thousands of years rather than millions. They all involve multiple killing mechanisms, not just one. During the Permian extinction, for instance, organisms faced global warming, ocean acidification, ocean anoxia, and possibly toxic gases released from the ocean all at once. The Chicxulub impact triggered darkness, cold, wildfires, tsunamis, and acid rain, a cascade of catastrophes. The extinctions also show that no group of organisms is immune. During different extinctions, different groups have been devastated. Marine organisms suffer more in some extinctions, terrestrial ones in others. Size doesn't consistently predict survival, neither does complexity or longevity or previous success. Adaptations that work well in normal times can become liabilities during extinctions. Specialization, which allows organisms to thrive in specific niches, becomes dangerous when those niches vanish. But extinctions also show the resilience of life as a whole. After each of these catastrophic events, life has recovered, diversified, eventually reaching or exceeding its previous diversity. The recovery takes millions of years, but it happens. new species evolve to fill the ecological roles left empty by extinct ones. Innovation occurs. The survivors diversify, experiment with new forms, new behaviours, new strategies. In some ways, extinctions clear the deck, removing dominant groups and allowing previously marginalised ones to flourish. After the Permian extinction, for instance, the surviving reptiles diversified into many new forms, including the ancestors of dinosaurs, crocodiles, and mammals. After the Cretaceous-Paleogene extinction, mammals, previously small and nocturnal, rapidly diversified into the vast array of forms we see today, from whales to bats to primates. Extinctions are catastrophic for individual species, for ecosystems, for the organisms living through them. But they're also, paradoxically, creative events in the long history of life, opening opportunities, driving innovation, reshaping the biosphere in ways that would never occur during stable times. And this pattern brings us to consider what the world looked like immediately after the Chicxulub impact, and how the survivors rebuilt ecosystems from the ashes of the old world. The world that emerges from the darkness is simplified, impoverished, but alive. The first plants to colonize the devastated landscape are pioneers, fast-growing species that can tolerate poor soil, variable conditions, full sunlight. Ferns spread rapidly, covering ground that was recently covered by complex forests. Some flowering plants, particularly those that produce large numbers of seeds, also expand quickly. The landscape is green again, but it's a different green, monotonous compared to the diversity that existed before. The surviving animals are mostly small. Mammals, freed from the pressure of dinosaur predation, begin to diversify. In the Cretaceous, mammals had been mostly small, nocturnal, insect-eating or seed-eating creatures that stayed hidden during the day. Now, with the dinosaurs gone, they begin to explore new possibilities. Some start eating plants more extensively. Some grow larger. No longer constrained by the need to hide, some become predators, filling the ecological roles left empty by the carnivorous dinosaurs. Birds, the surviving dinosaurs in a sense, also begin to diversify. The birds that survived the extinction were mostly small, generalized species. In the millions of years after the impact, they radiate into many new forms. Some evolve to fill the roles of ground-dwelling herbivores, others become specialized predators. The early Paleogene sees the evolution of large flightless birds in some regions, animals that briefly recapture some of the ecological space occupied by dinosaurs before mammals fully take over. The oceans recover more slowly. The phytoplankton populations bounce back relatively quickly once sunlight returns. But rebuilding complex marine food chains takes longer. Many of the specialized predators are gone, the mosasaurs and plesiosaurs that controlled the Cretaceous seas. The survivors, some sharks, some bony fish, some marine reptiles like sea turtles, begin to expand into the available ecological space. But it will take millions of years before ocean ecosystems reach the complexity and diversity they had before the impact. The climate in these first million years is unstable, recovering from the impact winter but not yet settled into a new equilibrium. There might be a period of warming as the greenhouse gases released during the impact, carbon dioxide from vaporized limestone, work their way through the climate system. Some evidence suggests temperatures actually spiked upward in the centuries after the impact, a brief hothouse period before settling back down. The carbon cycle, the movement of carbon between the atmosphere, oceans, and organisms, has been disrupted on a global scale. The massive die-off of plants removed a major carbon sink, the process by which living plants absorb carbon dioxide from the atmosphere. The burning of forests released enormous amounts of carbon back into the atmosphere. The ocean, with its collapsed ecosystems, also became less effective at absorbing carbon. All of this contributed to atmospheric carbon dioxide levels that were elevated compared to pre-impact conditions. But gradually, over thousands and tens of thousands of years, these systems begin to stabilize. The new plants growing across the landscape start absorbing carbon again. The ocean chemistry begins to normalize. Organisms start building shells again from calcium carbonate, locking carbon back into solid form. The climate settles into a new pattern, different from the Cretaceous in some ways, particularly in being more seasonal, more variable, but stable enough to support recovering ecosystems. The fossil record from this period shows a world in transition. The earliest Paleogene fossils show low diversity, simple communities, ecosystems that are clearly recovering from catastrophe. But as time passes, diversity increases. New species appear. The fossil assemblages become richer, more complex. By 1 million years after the impact, you can see the beginnings of the modern mammalian world. The radiation of groups that will eventually produce horses, whales, bats, primates, all the major lineages of mammals. There's a lesson here about recovery, about how life rebuilds after catastrophe. It's not instant, it's not a simple return to pre-impact conditions. The world that emerges is genuinely new, different in fundamental ways from what came before. The dominant animals are different, the plant communities are different, the climate is different. But life persists, adapts, diversifies, eventually creating ecosystems as complex and productive as those that were destroyed. And there's something worth contemplating in this pattern of destruction and renewal. The Chicxulub impact was a catastrophe, yes, killing most of what existed, ending lineages that had persisted for hundreds of millions of years. But it also created opportunities. Without the extinction, mammals might have remained small and nocturnal indefinitely, unable to compete with dinosaurs in most ecological roles. Without the extinction, the world might have continued essentially unchanged for millions more years, stable but static. The impact forced change, created space for innovation, allowed life to explore possibilities that would never have been available in the dinosaur-dominated world. It's not that the extinction was good. It wasn't. Suffering and death on that scale can never be called good, but it was, in a sense, creative, generative, a reset that allowed new forms of life to emerge. And this brings us to consider what the fossil record tells us about the dinosaurs themselves, the last days of their reign, and what we can learn from the evidence they left behind. In the final million years before the asteroid impact, dinosaurs were not in decline. This is an important point because there's sometimes a misconception that dinosaurs were already dying out, becoming less diverse, less successful, somehow evolutionarily exhausted. The fossil record tells a different story. Right up until the impact, dinosaurs were diverse, abundant, and in many ways at the peak of their success. The latest Cretaceous formations in North America, particularly in Montana and the Dakotas, preserve a rich dinosaur fauna. There are multiple species of hadrosaurs, the duck-billed dinosaurs, living in herds that might have numbered in the thousands. There are several species of ceratopsians, horned dinosaurs like Triceratops and Torosaurus, also living in herds, migrating seasonally across the landscape. The large predators, Tyrannosaurus and smaller raptors, are present in healthy populations, suggesting abundant prey. These formations also show us something of dinosaur behaviour and ecology. Some sites preserve nesting grounds, places where multiple individuals laid eggs in the same area, returning year after year. There's evidence of parental care, of adults staying with young animals, protecting and feeding them. Some dinosaurs were social, living in groups, cooperating in ways that suggest complex behaviour and communication. The diversity of dinosaurs in the late Cretaceous is impressive. In North America alone, there might have been 30 to 40 species of large dinosaurs, each occupying a specific ecological niche. Add in the smaller dinosaurs, the ones less likely to fossilise, and the total diversity might have been even higher. Globally, dinosaurs occupied every continent, every major ecosystem, from the Arctic to the Antarctic, from wetlands to deserts to forests. There's also evidence of ongoing evolution and innovation. New species were still appearing in the late Cretaceous. Tyrannosaurus itself is a relatively recent species, evolving just a few million years before the extinction. The specialized structures we see in late Cretaceous dinosaurs, elaborate crests on hadrosaurs, the massive horns and frills on ceratopsians, these suggest active sexual selection, populations healthy enough to invest energy in display structures and mating competitions. The plants dinosaurs depended on were also diverse and productive. The late Cretaceous sees the continued expansion of flowering plants, which by this time have diversified into many forms, from grasses to trees to shrubs. The landscape is productive, capable of supporting the enormous biomass of herbivorous dinosaurs. There's no indication of ecosystem collapse, no sign that the world dinosaurs inhabited was becoming unable to support them. So what happened when the asteroid hit was not a mercy killing of a group already in decline. It was the abrupt termination of lineages that were thriving, animals that could have continued to dominate terrestrial ecosystems for millions more years if left undisturbed. The dinosaurs didn't die because they were somehow unfit or outdated. They died because the world they were adapted to vanished in an afternoon. There's something tragic in this, something that resonates even across 66 million years. The dinosaurs had been successful for so long, had adapted to so many challenges, had survived previous climate changes and environmental disruptions. They had evolved remarkable diversity, occupied nearly every terrestrial niche, produced some of the largest, most impressive animals that have ever lived. And then, through no fault of their own, through no inadequacy or failure to adapt, they were destroyed by an event they couldn't predict, couldn't prepare for, couldn't survive. The last Triceratops that ever lived probably had no idea it was the last. It was just an animal, living its life, eating, breathing, existing in a world that seemed permanent. The last Tyrannosaurus, the final apex predator of the Mesozoic, didn't know it was witnessing the end of an era. These were just individual organisms trying to survive, to find food, to avoid danger, to pass on their genes to the next generation. They had no conception of extinction, no understanding that their entire lineage was about to end. And yet, in a sense, the dinosaurs didn't entirely die. Birds are dinosaurs, descended from small feathered theropods that lived in the Cretaceous. When we watch a robin or a hawk or a chicken, we're watching a dinosaur, a surviving lineage that made it through the extinction and diversified into the 10,000 species of birds alive today. The birds lost the ability to grow large, lost the ecological dominance their ancestors had, but they survived. They persisted. They're still with us. There's a kind of continuity in this, a thread connecting the Mesozoic to the present. The dinosaurs as we imagine them, the large spectacular animals that dominate our museums and our imagination, those are gone. But their descendants remain, living all around us, singing in trees, flying overhead, walking on beaches. They're smaller now, adapted to a world dominated by mammals, but they're still here, still dinosaurs in a technical sense, still carrying the genetic legacy of the Mesozoic. And this persistence, this thread of survival through catastrophe, brings us to consider what survival means, what extinction means, and how we should think about these concepts in the context of deep time. Extinction, at its simplest, is the death of the last individual of a species. Once that happens, the species is gone permanently. There's no bringing it back. No reservoir of genetic diversity hidden somewhere that might allow it to return. Extinction is final in a way that few other biological processes are. It's the complete and permanent removal of a unique lineage from the tree of life. For species, extinction is not like death for individuals. When an individual dies, others of its species continue. The genetic information, the ecological role, the evolutionary potential, all of these persist in the survivors. But when a species goes extinct, everything unique about it vanishes. The particular adaptations it evolved, the specific ecological role it filled, the potential it had to evolve into new forms, all of this is lost. In the case of the Chicxulub extinction, we're talking about the loss of thousands of species, perhaps tens of thousands, if we count all the small organisms that also vanished. Each of these species represented millions of years of evolutionary history, unique solutions to the problem of survival, genetic and morphological innovations that had never existed before and would never exist again. When they went extinct, all of that was lost. There's a concept in conservation biology called extinction debt, the idea that even after a catastrophic event, extinctions continue for some time afterward. Not all species die immediately. Some persist in reduced numbers, in isolated populations, clinging to existence in marginal habitats. But many of these survivors are doomed. Their populations are too small to be viable long term. They lack genetic diversity. They can't withstand additional stresses. They're the walking dead, extinction already determined even if the final individual hasn't died yet. After the Chicxulub impact, there were probably many species in this situation. They survived the immediate catastrophe, the darkness and cold and starvation, but they emerged into a world where they couldn't thrive. Their populations were too reduced, their habitats too damaged, their food sources too depleted. Over the following thousands or tens of thousands of years, these species went extinct, casualties of the impact even though they didn't die in the immediate aftermath. But extinction is not always a bad thing from an evolutionary perspective. It's a natural part of how evolution works. Most species that have ever existed are now extinct, perhaps 99% of all species that have lived. Extinction removes species that are less well adapted, creating opportunities for new species to evolve. It's part of the creative destruction of evolution, the constant churn of species appearing, existing for some period, and then vanishing, replaced by descendant species or by entirely new lineages. The difference with mass extinctions is that the selection isn't based on adaptation to normal conditions. It's based on the ability to survive extraordinary catastrophes. The species that made it through the Chicxulub impact weren't necessarily the best adapted to the late Cretaceous world. They were the ones that happened to have traits, small size, ability to hibernate, generalist diets, that allowed them to survive a few months of darkness and cold. This is essentially random selection relative to the traits that were advantageous before the impact. And this randomness has profound effects. It resets evolutionary trajectories. It eliminates dominant groups that might have continued to dominate indefinitely. It allows previously marginalized groups to expand and diversify. The mammals, for instance, were well adapted to being small and nocturnal in a dinosaur-dominated world. But these same traits allowed them to survive the impact and then, in the aftermath, to diversify into ecological roles they could never have accessed while dinosaurs were present. So the Chicxulub extinction, catastrophic as it was, also represents a kind of opportunity, a resetting of the evolutionary game board. It didn't destroy life. It didn't even come close to destroying all life. What it did was eliminate many successful lineages and create space for new ones to emerge. The world that came after was poorer in some ways, lacking the spectacular diversity of Cretaceous ecosystems, but it was also richer in potential, open to evolutionary innovations that would eventually produce the world we know today. There's a philosophical dimension to all of this that's worth contemplating quietly. The dinosaurs existed for more than 160 million years. Humans, in our modern form, have existed for perhaps 300,000 years. Recorded human history covers about 5,000 years. The entire span of human civilization is less than 1/10,000th the duration of dinosaur reign. They were successful in ways we can barely comprehend, surviving for time scales that dwarf human experience, and yet they ended. Not gradually, not through slow decline, but suddenly, completely. All the non-avian lineages gone in what amounts to an instant in geological time. There's a lesson here about impermanence, about how even the most successful adaptations, the most dominant groups, can vanish, when conditions change drastically enough. Nothing is permanent. Everything eventually ends or transforms into something else, and this impermanence is not a flaw in the system. It's a feature, the mechanism by which life adapts to a changing planet, by which new forms emerge and old ones gracefully or catastrophically make way. And this understanding brings us to consider how we know what we know about these ancient events, and what the limits of our knowledge are. For all that we've learned about the Chicxulub impact and the extinction it caused, there's much we still don't know, and, in some cases, can never know. The past is not directly accessible to us. We can't observe it, can't visit it, can't run experiments on it. All we have are the traces left behind, the fossils, the rocks, the chemical signatures, and from these fragments, we attempt to reconstruct events that happened millions of years ago. The fossil record, rich as it is fundamentally incomplete. Most organisms that die don't fossilize. They're eaten, decomposed, scattered by scavengers. Fossilization requires specific conditions, rapid burial in sediment, protection from scavengers, the right chemistry to preserve bones or shells. Only a tiny fraction of organisms that ever lived have left fossils, and only a tiny fraction of those fossils have been found. This means there are entire groups of organisms we know little or nothing about. Soft-bodied creatures, small organisms, things that lived in environments that don't preserve fossils well, all of these are underrepresented or absent from the fossil record. We know about the large dinosaurs because their bones fossilize relatively well. But what about the small dinosaurs, the insects, the worms and soft-bodied invertebrates? Most of these are lost, their existence erased by time and decomposition. Even for the groups we know about, our knowledge is fragmentary. We might have a few bones from a particular species, enough to name it and place it in the evolutionary tree, but not enough to understand its behaviour, its ecology, its full range of variation. Many dinosaur species are known from single specimens, sometimes from partial skeletons. We make educated guesses about what they looked like, how they lived, based on comparisons with related species and modern animals, but these are always uncertain. The conditions during and immediately after the impact are also difficult to reconstruct with precision. Computer models can simulate the impact, the ejection of material, the global wildfires, but these models depend on assumptions about atmospheric composition, about the angle and velocity of the asteroid, about the specific rock types at the impact site. Small changes in these parameters can produce significantly different results. We have ranges of possibility rather than exact certainties. The timeline of events is similarly uncertain. We know the impact happened 66 million years ago, but the precision of radiometric dating at these timescales is limited. The uncertainty is typically a few tens of thousands of years, which sounds small but is actually quite long in terms of biological and ecological processes. Did ecosystems collapse instantly? Or did it take centuries? Did the darkness last months or years? Did temperatures recover quickly or slowly? These questions have answers, but the answers come with error bars, with ranges of uncertainty. There are also questions that might be fundamentally unanswerable given the evidence available. For instance, did any non-avian dinosaurs survive for thousands of years after the impact in isolated refuges? The fossil record can't definitively answer this. Finding evidence of absence is difficult. The lack of fossils might mean a species was extinct, or it might just mean we haven't found the fossils yet. Some areas are well studied, well sampled, others are remote, inaccessible, geologically complex. There could be fossils we'll never find, and there are questions about subjective experience that we can never answer. What was it like to be a dinosaur in those final hours? Did they suffer? Were they frightened? These questions are emotionally compelling but scientifically unanswerable. We can describe the physical effects of the impact, the temperature, the light levels, the environmental conditions, but consciousness, suffering, fear, these internal states leave no fossils. No chemical signatures, no evidence we can study. This doesn't mean the scientific study of the past is futile or purely speculative. Far from it. The accumulation of evidence from multiple sources, the development of new analytical techniques, the testing of hypotheses against the fossil and geological record, all of this has produced robust, reliable knowledge about what happened. The broad outlines of the Chicxulub impact story are well established, supported by multiple lines of evidence, confirmed by independent studies. But within that overall framework, there's uncertainty, nuance, ongoing debate about details. This is normal in science. It's how the process works. We establish what we can with high confidence, acknowledge what remains uncertain, and continue working to refine our understanding. The humility to admit what we don't know is as important as the confidence to assert what we do know. And there's something satisfying about this acceptance of limits. We've reconstructed an event from 66 million years ago in remarkable detail that would have seemed impossible just a few decades ago. We've identified the asteroid, found the crater, mapped the global effects, understood the killing mechanisms. That's an extraordinary achievement, a testament to human curiosity and scientific rigour. But we've also learned the limits of that knowledge, the uncertainties that persist, the questions that may never have definitive answers, and that's okay. Mystery is not a failure of science. It's an invitation to continued exploration, to new questions, to deeper understanding. And this balance between what we know and what remains unknown brings us into the final act of our journey, where we move from facts toward meaning, from science toward philosophy, from the specific event toward what it tells us about change, survival, and our own place in the long story of life on Earth. 66 million years is a duration almost impossible for the human mind to grasp. Let's try to put it in perspective to understand the depth of time we're talking about when we discuss the extinction of the dinosaurs and the world that came after. If we compress Earth's entire history into a single year, with the planet forming on January 1st, the Chicxulub impact happens around December 25th, Christmas Day in this compressed timeline. The dinosaurs dominated for roughly 4 days, from December 21st to December 25th. Humans, modern humans, appear in the final minutes before midnight on December 31st. All of recorded human history, from the first writing systems to the present, occupies the last few seconds. Another way to think about it, if you could go back in time at a rate of 1 year per second, it would take more than 2 years of constant travel to reach the Chicxulub impact. You'd pass through all of human history in the first few seconds. You'd cross the entire Ice Age, the evolution of modern humans, the extinction of Neanderthals, all within the first 10 minutes. And then you'd spend the next 2 years travelling backward through the Cenozoic era, the age of mammals, watching species evolve and go extinct, continents drift, climates shift, before finally arriving at that moment 66 million years ago when the sky caught fire. The dinosaurs existed for more than 160 million years. If we use the same 1 year per second time travel, it would take more than 5 years to travel from the Chicxulub impact back to the first dinosaurs. That's longer than most people spend in college. Imagine travelling continuously for 5 years, never stopping, never arriving, just moving backward through deep time, watching the dinosaurs evolve and diversify and adapt to countless environmental changes. This vast expanse of time is difficult to hold in your mind because human experience operates on such different scales. We think in terms of days and years, perhaps decades if we're planning long term. The oldest human structures are a few thousand years old. The oldest human fossils are a few 100,000 years old. But the processes we're discussing, evolution, extinction, the movement of continents, these operate on scales of millions of years. They're too slow to see directly, too gradual to perceive within a human lifetime. And yet, despite these enormous timescales, the Chicxulub impact happened in an instant. 66 million years of dinosaur evolution, all the accumulated adaptations, all the species that had ever existed in the Mesozoic, all of it was ended in a single afternoon by an object that took only a few seconds to pass through the atmosphere and strike the Earth. The contrast between the slow pace of evolution and the sudden violence of extinction is stark, almost incomprehensible. This contrast tells us something important about how change happens in natural systems. Most of the time, change is gradual. Species evolve slowly, adapting incrementally to changing conditions. Continents drift at rates measured in centimetres per year. Climate shifts over thousands or tens of thousands of years. These are the normal processes, the background rate of change that life can adapt to through natural selection. But occasionally, rarely but inevitably over geological time, change happens suddenly. An asteroid hits, a supervolcano erupts. An ice age begins or ends with unusual rapidity. These events overwhelm the ability of most species to adapt. They're too fast, too extreme, too far outside the range of conditions the species evolved to handle. And when this happens, extinction rather than adaptation becomes the dominant outcome. The dinosaurs were exquisitely adapted to the late Cretaceous world. They had evolved over millions of years to thrive in warm climates, in ecosystems with high primary productivity, in stable conditions that persisted for geological ages. But all those adaptations became irrelevant when the world changed in an afternoon. Size, which had been advantageous for millions of years, suddenly became a liability. Specialization, which had allowed different species to efficiently exploit specific niches, became a death sentence when those niches vanished. There's a mathematical concept called the recurrence time, the average interval between events of a given magnitude. For asteroid impacts the size of Chicxulub, the recurrence time is roughly 100 million years. This doesn't mean impacts happen regularly every 100 million years. They're random. You could have 2 impacts separated by 1 million years, then 200 million years with none. But on average, over the deep history of Earth, large impacts happen about once every 100 million years. This means that for most of Earth's history, for most of the time life has existed, conditions are relatively stable. Evolution proceeds, life diversifies, ecosystems become complex, and then, at unpredictable intervals, catastrophe strikes, resetting everything, forcing life to start over in many ways. This pattern of gradual change, punctuated by sudden catastrophes, is fundamental to understanding Earth's history and the history of life on our planet. And sitting here now, 66 million years after the most recent major impact, we're living in one of those intervals of relative stability. The mammals, our lineage, arose from the ashes of the Cretaceous and diversified into countless forms. Humans evolved, developed consciousness, language, civilization. We've built a world of our own, a technological civilization that in some ways insulates us from natural processes. But we're still subject to those processes, still vulnerable to changes we can't control or predict. The asteroid that killed the dinosaurs was not the last large object to threaten Earth. Others will come, eventually, inevitably. And when they do, the question will be whether our intelligence, our technology, our ability to predict and possibly prevent impacts will save us where the dinosaurs' strength and success could not save them. And this question brings us to consider what the extinction tells us about our own vulnerability, and what lessons we might learn from events that happened long before humans existed. The story of the Chicxulub impact is not just ancient history. It has direct relevance to our current situation, to the challenges we face as a species and as a civilization. The parallels are not exact. The differences are significant. But there are lessons here worth considering carefully. The most obvious lesson concerns asteroid impacts themselves. The Chicxulub impact demonstrated that these events, while rare, are catastrophically destructive when they occur. Since we became aware of this threat in the 1980s and 90s, humanity has taken steps to identify and track potentially hazardous asteroids. We've catalogued most of the large objects that could cause global catastrophe. And we're working on cataloguing the smaller but still dangerous ones. We've also developed, at least in theory, the capability to deflect asteroids if we detect them early enough. The DART mission, which successfully altered the orbit of a small asteroid in 2022, demonstrated that this is technically feasible. We're not helpless against this threat the way the dinosaurs were. We have warning systems, we have technology, we have the ability, if we choose to use it, to protect ourselves from a fate that eliminated the dominant species on Earth 66 million years ago. But the impact also teaches us about vulnerability to rapid environmental change more generally. The dinosaurs didn't die from the impact itself, not most of them. They died because their environment changed too quickly for them to adapt. The lesson here is not specifically about asteroids, but about the danger of rapid change to complex systems that have evolved under stable conditions. Our own civilization is, in many ways, exquisitely adapted to current conditions. We've built agricultural systems optimized for current climate patterns, current rainfall patterns, current temperature ranges. We've built coastal cities assuming current sea levels. We've developed supply chains, infrastructure, economies, all based on assumptions about environmental stability. If those conditions change rapidly, many of these systems could fail. Climate change is the most obvious example. The rate of change we're currently experiencing is fast by geological standards, faster than most species can adapt through natural selection. We're conducting an unintentional experiment in how quickly Earth's climate can change and what the consequences are for ecosystems and human societies. The Chicxulub impact tells us that rapid environmental change is dangerous, that ecosystems collapse when pushed too far too fast, that even successful, well-adapted species can go extinct when the world they're adapted to vanishes. The extinction also demonstrates the importance of biodiversity. The ecosystems that recovered best after the impact were those that retained the most diversity of surviving species. Diverse ecosystems are more resilient. They have more redundancy, more backup options, more potential for adaptation. When we reduce biodiversity today, when we eliminate species or simplify ecosystems, we're reducing the resilience of those systems, making them more vulnerable to future shocks. There's also a lesson about the interconnectedness of systems. The Chicxulub impact triggered a cascade of effects. The initial impact caused wildfires. The wildfires created smoke and soot. The soot blocked sunlight. The darkness killed plants. The plant deaths killed herbivores. The herbivore deaths killed carnivores. One event triggered a chain reaction that eventually touched every ecosystem on Earth. This tells us that systems are connected in ways that aren't always obvious. That disrupting one part of a system can have far-reaching effects throughout the whole. But perhaps the deepest lesson is about humility. The dinosaurs were successful for longer than any other group of land animals. They adapted to countless challenges over more than 100 million years. They survived climate changes, continental movements, sea level fluctuations, volcanic eruptions. They were, by any reasonable measure, extraordinarily successful. And yet they ended, completely and suddenly, through an event they couldn't predict or prevent. We're successful now. Human civilization has achieved things that would have seemed impossible to our ancestors. We've understood physics, cured diseases, communicated across the globe instantly, sent machines to other planets. Our technology gives us capabilities no other species has ever had. But we're not invulnerable. We're not exempt from the forces that have shaped life throughout Earth's history. We're subject to the same physical laws, the same environmental constraints, the same possibility of catastrophic change. This doesn't mean we're doomed. The dinosaurs had no way to detect an incoming asteroid, no way to change its trajectory, no way to protect themselves. We do. We have knowledge they lacked. We have technology they never developed. We have the ability to understand threats and potentially prevent them, but we also have the ability to create new threats. To change our environment in ways that might be as catastrophic as an asteroid impact, just slower and more predictable. The choice of what to do with this knowledge, this capability, is ours to make. We can use our understanding of Earth's history to inform our decisions about the future. We can recognize that our current success, like the dinosaurs' success, is not permanent and requires active protection. We can work to prevent catastrophes that are within our power to prevent, to prepare for ones we can't prevent, to build systems that are resilient rather than fragile. The Chicxulub impact happened 66 million years ago, but its lessons are timeless. Change is inevitable. Catastrophes are possible. Success is no guarantee of survival. Adaptation requires flexibility. And intelligence, knowledge, the ability to learn from the past, these might be our best tools for navigating an uncertain future. And this understanding of our place in the larger pattern of life on Earth brings us to consider what happened to the world after the extinction and how the recovery process unfolded over millions of years. The recovery from the Chicxulub impact was not a simple process of life bouncing back to pre-impact conditions. It was a fundamental reorganization of Earth's ecosystems, a rebuilding that took millions of years and produced a world genuinely different from what had existed before. In the first 100,000 years after the impact, the world remained relatively impoverished. The surviving species were expanding their populations, spreading into available territories, but diversity remained low. The ecosystems were simple, lacking the complex food webs and specialized relationships that characterized the late Cretaceous. It was a world in recovery, alive but diminished. The plants led the recovery, as they almost always do after environmental catastrophes. Fast-growing opportunistic species colonized the landscape first, taking advantage of the abundant light and the lack of competition. Ferns were particularly successful in many areas, creating fern prairies where diverse forests had once stood. This fern spike, as it's called in the fossil record, is visible in rock formations around the world, a layer dominated by fern spores just above the impact boundary. But gradually, other plants returned. Flowering plants, which had diversified significantly in the late Cretaceous, began to recover and expand. Trees started to appear again, first fast-growing pioneer species, then slower-growing ones that could eventually dominate forests. The plant communities that developed were different from those of the Cretaceous, but they were functional, productive, capable of supporting animal life. The animals followed the plants. Mammals, freed from competition with and predation by dinosaurs, began to diversify rapidly. In the Cretaceous, nearly all mammals had been small, most weighing less than a kilogram. Within a few million years of the extinction, there were mammals the size of large dogs. Within 10 million years, there were mammals as large as bears. The ecological space left empty by the dinosaurs was being filled, but by an entirely different group of animals. Some of these early mammals were herbivores, browsers eating the recovering vegetation. Others were carnivores, preying on the herbivores. Some were insectivores, omnivores, specialized for specific diets or lifestyles. The radiation of mammals in the Paleogene is one of the most spectacular examples of adaptive radiation in the fossil record. A single group diversifying into dozens of families, hundreds of genera, thousands of species over a relatively brief period. Birds were also diversifying, though perhaps more slowly than mammals. The birds that survived the extinction were mostly small, generalized species, but their descendants began to explore new possibilities. Some evolved to become ground-dwelling herbivores, occupying niches left empty by the dinosaurs. Others became specialized predators. Still others remained small and arboreal, living in the recovering forests. The oceans recovered more slowly than the land, as is often the case after mass extinctions. Marine food chains are typically longer and more complex than terrestrial ones, with more trophic levels between the primary producers and the top predators. Rebuilding these complex chains takes time, but gradually, over millions of years, ocean ecosystems recovered their diversity and productivity. New groups of organisms evolved to fill niches left empty by the extinction. In the oceans, whales evolved from land-dwelling ancestors and became the dominant large predators, replacing the mosasaurs. Seals and other marine mammals also evolved, occupying ecological roles that had been filled by various reptiles in the Mesozoic. On land, predatory mammals replaced the tyrannosaurs and raptors, while large herbivorous mammals replaced the ceratopsians and hadrosaurs. But the world these animals inhabited was different from the Mesozoic in fundamental ways. The climate was more seasonal, with greater temperature variation between summer and winter, and between different latitudes. This seasonality favoured animals that could adapt to changing conditions, that could migrate or hibernate or adjust their behaviour with the seasons. Many mammals developed such abilities, while the dinosaurs, adapted to the more stable Mesozoic climate, had not needed them. The continents had also continued to drift. By 10 million years after the impact, the geography of Earth was noticeably different from the late Cretaceous. The Atlantic Ocean was wider. India was approaching Asia, though the collision that would form the Himalayas was still millions of years away. These changing geographies influenced climate patterns, ocean currents, the distribution of species. Forests changed too. The conifers that had dominated many Mesozoic forests declined in importance, replaced by flowering plants that were better adapted to seasonal climates. Grasslands evolved, creating new ecosystems that had never existed in the Mesozoic. These grasslands would eventually support vast herds of herbivorous mammals, creating ecosystems somewhat analogous to the dinosaur-dominated landscapes of the Cretaceous, but structured quite differently. By 30 million years after the impact, by about 36 million years ago, the world had recovered much of its pre-impact diversity, though the specific species were entirely different. Ecosystems were complex again, food chains were long again, the productivity of the biosphere had returned to pre-impact levels. The catastrophe was over, not forgotten. The evidence remained in the rocks, but ecologically the world had moved on. And there's something profound in this recovery, this demonstration of life's resilience. The Chicxulub impact was one of the most devastating events in Earth's history, but it didn't end life. It didn't even come close to ending life. What it did was reset the dominant groups, clear space for new innovations, allow evolution to explore possibilities that had been closed off by the success of the dinosaurs. The world that emerged was different, but it was also rich, diverse, and in many ways just as successful as the world that had been destroyed. And this pattern of destruction and renewal, of endings that are also beginnings, brings us to consider what all of this means for how we think about change, permanence, and the long arc of life on Earth. Let's settle into a more philosophical space now, and contemplate what the Chicxulub extinction teaches us about impermanence and transformation. The story we've been exploring is, at its heart, a story about how nothing lasts forever, how even the most successful adaptations eventually end, how endings can also be beginnings. The dinosaurs dominated terrestrial ecosystems for more than 160 million years. During that time, they evolved into thousands of species, filled nearly every ecological niche on land, adapted to countless environmental changes. They were, by any measure, one of the most successful groups of organisms in Earth's history, and yet they ended. Not slowly, not through gradual replacement by better adapted competitors, but suddenly, catastrophically, in an event that was essentially random from their perspective. There's a Buddhist concept of impermanence, the idea that all things, all phenomena, all states of being are temporary. Nothing remains unchanged. Everything that arises eventually passes away. The extinction of the dinosaurs is a stark illustration of this principle. Even success on a geological timescale is temporary. Even adaptations that work for millions of years eventually become irrelevant when conditions change sufficiently. But impermanence is not the same as meaninglessness. The dinosaurs' reign was not meaningless just because it ended. During their time on Earth, they were here, alive, experiencing existence in whatever way dinosaurs experienced it. They ate, they reproduced, they interacted with their environment and each other. They were subjects of life, not just objects in the fossil record. Their existence had meaning while they existed, even if that existence was ultimately temporary. And their ending was not a complete ending. The dinosaurs transformed rather than simply vanishing. Their descendants, the birds, survived and diversified. The ecosystems they had shaped, the evolutionary pressures they had created, the ecological relationships they had formed, all of these influenced what came after. The mammals that diversified in the Paleogene were shaped by their long coexistence with dinosaurs, by the evolutionary pressures of avoiding dinosaur predators, of competing for resources in a dinosaur-dominated world. This is transformation rather than obliteration. The Mesozoic ended, yes, but it didn't disappear without a trace. It shaped what came after. The Cenozoic era, the age of mammals, is partially a product of the Mesozoic, influenced by it, built on foundations laid during it. There's continuity even in catastrophic change, connections that persist across extinction boundaries. The same is true for the planet itself. The Chicxulub impact changed Earth's surface, created the massive Chicxulub crater, scattered debris globally, disrupted the carbon cycle and climate system. But Earth recovered. The crater was buried under younger sediments. The climate stabilized. The carbon cycle returned to balance. The planet healed, given enough time. The scars remain in the geological record, but the functioning of Earth as a system was not permanently damaged. This resilience, this ability to recover from catastrophe, is built into natural systems. Ecosystems have redundancy, multiple species filling similar roles, so that if one goes extinct, others can expand to fill the gap. The carbon cycle has multiple feedback mechanisms that work to stabilize atmospheric carbon dioxide over long-time scales. Life itself has extraordinary diversity, not just in terms of species, but in terms of strategies, adaptations, ways of making a living. This diversity ensures that no single catastrophe can eliminate everything. But resilience doesn't mean invulnerability. Systems can be pushed too far. Catastrophes can overwhelm recovery mechanisms. The Permian extinction, the Great Dying, came much closer to eliminating all complex life than the Chicxulub impact did. The recovery from that event took millions of years longer, and some ecosystems, like the Permian coral reefs, never returned in their original form. They were permanently changed, transformed into something different. There's a balance here, a middle path between despair and complacency. Life is resilient but not infinitely so. Change is constant but not always catastrophic. Endings are inevitable, but they're also beginnings. The key is to hold all of these truths simultaneously, to recognize both the vulnerability and the persistence of life, the temporary nature of all things, and the continuity that persists through change. For the dinosaurs, the Chicxulub impact was an ending. For the mammals, it was a beginning. For Earth, it was a transition, a moment of transformation in a history spanning billions of years. None of these perspectives is wrong. They're all true simultaneously. The event was catastrophic and creative, destructive and generative, an ending and a beginning depending on your point of view. And perhaps this is the deepest lesson of the extinction. Events don't have single, simple meanings. They're complex, multifaceted, containing within them elements of tragedy and opportunity, destruction and creation. The challenge is to see the fullness of this complexity, to resist the urge to simplify, to embrace the paradox that endings are also beginnings, and that transformation, while painful, is also how life continues. The dinosaurs are gone, but birds fill the skies. The Mesozoic ended, but the Cenozoic followed. The world that was destroyed was also the world that made possible the one we inhabit now. There's a continuity in this, a thread that connects past to present to future, that suggests that change, while inevitable and sometimes catastrophic, is also the mechanism by which life persists, adapts, and continues to exist on a planet that is itself constantly changing. And this understanding of continuity through change brings us to consider why we remember the dinosaurs, why we tell their story, and what their extinction means to us now, 66 million years later. There's something profound in the fact that we remember the dinosaurs at all. They lived and died millions of years before any human existed. They left no art, no buildings, no conscious legacy. They were animals, living their lives, unaware that one day creatures they could never have imagined would discover their bones and reconstruct their existence. And yet we remember them, we study them, we name them, we build museums to house their fossils, we make films about them, we teach children about them. Why? Part of the answer is simply wonder. Dinosaurs were remarkable animals. Unlike anything alive today in size and form and the sheer strangeness of their existence. There's something captivating about the idea of a world where 30-ton animals walked the earth, where predators as large as buses hunted prey through forests of unfamiliar plants. It's exotic, alien, a window into a world that was genuinely different from our own. But there's more to it than just spectacle. The dinosaurs represent deep time, geological ages, timescales so vast that they challenge our intuitive understanding of time itself. When we learn about the dinosaurs, we're learning that the world was not always as it is now, that the present is just one moment in a vastly longer story, that the Earth has a history that extends far beyond human experience. This perspective is both humbling and liberating. It's humbling because it reminds us how brief our time on Earth has been, how recent human civilization is, how temporary our current dominance might be. If the dinosaurs, successful for more than 160 million years, could end, then certainly human civilization, existing for mere thousands of years, is not guaranteed permanence. But it's also liberating because it demonstrates that change is possible, that the world can be fundamentally different, that the current state of things is not the only possible state. The mammals were small and marginal for most of the Mesozoic. The dinosaurs seemed permanent, dominant, unassailable. And then they ended, and the mammals' opportunity came. The world transformed. What seemed permanent was revealed to be temporary. What seemed marginal became dominant. This carries a message of possibility. The way things are now is not how they must always be. Systems that seem stable can change. Dominant groups can be replaced. The future might be very different from the present, just as the present is very different from the Cretaceous. This is relevant not just in evolutionary terms, but in human terms, in thinking about social systems, economic structures, political arrangements, all the things we sometimes imagine are permanent, but are actually as temporary as the reign of the dinosaurs. We remember the dinosaurs also because their story is our story in a sense. We're mammals. Our ancestors were small nocturnal creatures living in the shadow of the dinosaurs. They survived the Chicxulub impact, possibly by chance, possibly by having adaptations that proved useful in that particular catastrophe. And from those survivors, over 66 million years, evolved all the mammals we know today, including humans. Without the extinction, humans might never have evolved. The ecological space for large, intelligent, terrestrial mammals didn't exist while dinosaurs dominated. Our ancestors might have remained small and marginal indefinitely. The asteroid that killed the dinosaurs was, in a sense, the event that made human existence possible. We're here because they're not, because the world was reset, because evolution got a chance to explore new possibilities. This creates a strange kind of debt, or perhaps just an acknowledgement of contingency. Our existence depends on catastrophes that happened long before we evolved, on random events like asteroid impacts, on the specific sequence of extinctions and radiations that led eventually to primates, to humans, to consciousness and civilization. We're not the inevitable product of evolution. We're one possible outcome among many, the result of a particular series of events that could easily have unfolded differently. The dinosaurs also teach us about loss. Thousands of species that existed in the late Cretaceous are now gone permanently. We know some from fossils can reconstruct something of what they looked like and how they lived. But there's much we can never know. What colours were they? What sounds did they make? How did they interact? What was their subjective experience of existence? These questions have no answers. The information is lost, erased by time and extinction. This reminds us that loss is real, that when something goes extinct, it's gone in a way that's different from other kinds of loss. A building can be rebuilt, a book can be reprinted, but a species, once extinct, cannot be brought back. The information encoded in its genes, shaped by millions of years of evolution, is lost permanently. This makes extinction different from other forms of destruction, more final, more absolute. And yet we preserve memory. We dig up fossils, study them, try to understand what was lost. We reconstruct extinct animals, make models, paint pictures, create exhibits. We tell stories about them, imagine what their world was like. This is a kind of remembrance, a way of acknowledging that they existed, that they mattered, that they were part of Earth's story even though they're no longer part of Earth's present. There's something touching in this effort, in the care with which scientists reconstruct extinct organisms, in the wonder with which children look at dinosaur skeletons, in the collective human fascination with these ancient animals. It's a kind of mourning, perhaps, or a kind of celebration, or maybe both. We remember what was lost. We honour it by studying it. We keep it alive in some form by refusing to forget. The dinosaurs existed. They dominated the Earth for more than 160 million years. They evolved into forms both familiar and bizarre. They lived, reproduced, competed, cooperated, experienced the world in ways we can only dimly imagine. And then they ended suddenly and catastrophically in an event they couldn't prevent or predict. We remember them not just because they're fascinating, though they are, but because their story is connected to our story, because their ending made our beginning possible, because in understanding them we understand something about life, time, change, and our own place in the long, ongoing story of Earth. And this brings us finally to the close of our journey, to a time of reflection on what we've explored and what it means to contemplate events from 66 million years ago on a quiet night in the present. We're moving now into the final section of our journey, where facts gradually give way to reflection, where science becomes philosophy, where the specific event opens onto larger questions about existence, change, and meaning. Let's settle more deeply now. Let the information we've explored find its place, and consider what comfort we might find in contemplating deep time. There's a paradox in thinking about the extinction of the dinosaurs. On one hand, it's a catastrophic event, the destruction of entire ecosystems, the death of most species on Earth, suffering on an almost incomprehensible scale. On the other hand, it happened 66 million years ago. The immediate suffering is long over. The Earth recovered. Life continued. New forms evolved. The catastrophe, while real, is also distant, removed from us by time so vast that the emotional sting is dulled by sheer temporal distance. This paradox reveals something interesting about how we relate to events at different timescales. Recent suffering within human memory, evokes immediate emotional response. We can imagine it, relate to it, feel empathy for those who experienced it. But suffering from millions of years ago, while intellectually acknowledged, doesn't carry the same emotional weight. It's too distant, too abstract, too removed from our direct experience, and there's something peaceful in this distance. When we contemplate the Chicxulub impact, we're not agonizing over immediate tragedy. We're reflecting on an event that's complete, concluded, fully resolved by time. The dinosaurs died, but that dying is over. The darkness came, but it lifted. The world was devastated, but it recovered. From our perspective, 66 million years later, we can see the whole arc, the destruction and the recovery, the ending and the beginning, the catastrophe and the renewal. This long view, This ability to see events in the context of deep time provides a kind of comfort that's different from the comfort we find in thinking about shorter timescales. It's not that suffering doesn't matter, it does, but it's temporary, part of a larger pattern, contained within a framework of time that eventually heals all wounds, not through making them meaningless, but through continuing past them, allowing new things to emerge. The dinosaurs' extinction reminds us that nothing is permanent, but it also reminds us that impermanence is okay. The dinosaurs existed for their time, had their era, lived and thrived for millions of generations. Their ending doesn't erase that existence, doesn't make it meaningless. It just means it was temporary, as all things are. And after them came something else, equally valid, equally real, equally temporary in the long run. This applies to everything. Not just extinct animals. The Cretaceous period existed for 79 million years and then ended. The Cenozoic era has existed for 66 million years and will eventually end too. Each geological period, each epoch, each age has its time and then passes, replaced by something new. This isn't tragedy. It's just the pattern of how time works, how the universe operates, how change happens. For us, living our brief human lives, this long perspective can be calming. The problems we face, the anxieties we carry, the challenges that seem overwhelming, all of these exist within a larger context of time that will eventually move past them. Not that our problems don't matter, they do, in the immediate sense to us, in our time. But they're also temporary, part of a moment that will pass, contained within a flow of time that will continue long after our specific concerns have been resolved one way or another. The Earth has experienced 5 major mass extinctions. It survived asteroid impact, supervolcano eruptions, climate changes far more extreme than anything humans have experienced. It's been nearly completely frozen, nearly completely molten, nearly completely anoxic, and yet it's still here, still supporting life, still beautiful and complex and filled with countless forms of existence. The resilience of the planet on these timescales is profound, almost comforting in its reliability. This doesn't mean we shouldn't care about conservation, about protecting species, about preventing environmental damage. We should. The loss of species is real and matters. But it means we can have perspective, can recognize that life as a phenomenon is more resilient than any individual species or ecosystem, that the story will continue even as specific chapters end, that the long arc bends toward continuation rather than cessation. There's a meditation practice in some traditions that involves contemplating impermanence, really sitting with the reality that everything changes, everything ends, everything passes. The Chicxulub impact offers a kind of focal point for this practice. An entire world ended. The most successful group of land animals in Earth's history vanished. And yet, here we are, the planet is fine, life continues, new forms exist where old ones vanished. The impermanence is real, but it's not the end of the story. It's just a transition, a transformation, a movement from one state to another. And perhaps this is the comfort in deep time. It shows us that endings are survivable, that catastrophes are temporary, that the flow of existence continues through and past individual events, no matter how dramatic. The dinosaurs ended, but life didn't end. The Cretaceous ended, but time didn't end. The world was devastated, but the world recovered. And this pattern, this resilience, this continuation, extends backward through billions of years and forward into a future we can't predict, but can trust will continue in some form. And this trust in continuation brings us to consider what it means to live in the shadow of the dinosaurs, to be the inheritors of the world their extinction created. We live in a world shaped by extinction, built on the ashes of the Cretaceous. Every ecosystem we know, every mammal we encounter, every bird in the sky exists because the dinosaurs vanished 66 million years ago. We're inheritors of that catastrophe, beneficiaries of an event that was devastating for the species that experienced it, but ultimately creative in its long-term effects. The mammals that survived the Chicxulub impact were small, mostly weighing less than a kilogram. They were adapted to the margins, to life in the shadows, to making a living in a world dominated by much larger, more powerful animals. But when those larger animals vanished, the mammals found themselves in a world of opportunity. Ecological niches were empty. Food resources were abundant once the ecosystems recovered. There were no major predators to limit their expansion, and so the mammals radiated, diversified, evolved into forms that would have been impossible while dinosaurs dominated. They grew larger, filling the roles of large herbivores and large carnivores. They became more diverse, adapting to nearly every terrestrial habitat on Earth. They evolved complex behaviors, social structures, intelligence. Over millions of years, the mammalian radiation produced primates, and primates eventually produced humans. We are, in a very real sense, children of the impact. Our lineage exists because of that catastrophe. The specific sequence of events that led to human evolution depended on the extinction of the dinosaurs, on the opening of ecological space for mammalian diversification, on the particular environmental conditions of the Cenozoic era. Change any of these factors significantly and humans might never have evolved. This creates an interesting moral and philosophical situation. We benefit from an event that caused immense suffering. The dinosaurs died, entire ecosystems collapsed, countless individual organisms experienced fear and pain and death. And from that suffering eventually came us. How should we feel about this? Gratitude seems inappropriate given the cost. Guilt is absurd since we had no role in causing the event. Perhaps the right response is simply acknowledgement, recognition that our existence is contingent on catastrophes we didn't choose and couldn't control. But there's also responsibility in being inheritors. We didn't create the world we live in, but we maintain it, shape it, have power to affect it in ways that no previous organisms have had. The dinosaurs couldn't have prevented their extinction. They had no capacity to detect asteroids, no technology to deflect them, no ability to alter the trajectory of cosmic events. We do. We have knowledge they lacked, tools they never developed, the ability to see catastrophes coming and potentially prevent them. This creates an obligation, perhaps, to use that ability wisely. We inherited a world shaped by catastrophe. We have the power to inflict new catastrophes or to prevent them. The choice of which path to take is ours in a way it never was for previous organisms. We're not just subject to evolution anymore. We're active participants in shaping the biosphere, in determining which species survive and which go extinct, in altering environments on a global scale. The current extinction rate, driven by human activity, is estimated to be 100 to 1,000 times higher than the background rate, the normal rate of extinction that occurs in the absence of catastrophes. We're not causing a Chicxulub-scale mass extinction, not yet. But we're certainly causing an elevated extinction rate that will be visible in the fossil record millions of years from now. Future geologists, if any exist, will be able to see our impact on biodiversity. We'll be able to identify the late Holocene as a period of unusual extinction rates. This is our legacy as inheritors. We received a world recovering from ancient catastrophes. We've built a civilization on the foundation of that recovery. And now we're shaping the world in ways that will affect its future as much as the Chicxulub impact affected the past. The question is whether we'll be remembered as wise stewards or as a brief destructive phenomenon, a species that had immense power but used it poorly. The dinosaurs had no choice in their extinction. It was imposed on them by external forces, by cosmic chance, by an asteroid whose trajectory was set millions of years before it struck Earth. But we have choices. We can choose to protect biodiversity or to allow it to decline. We can choose to stabilize our climate or to let it change drastically. We can choose to use our knowledge and technology to create a sustainable civilization, or to exhaust our resources and collapse. These choices are not easy. They require balancing immediate needs against long-term consequences, individual interests against collective welfare, economic growth against environmental sustainability. But they're choices nonetheless, moral decisions with real consequences for the biosphere we inhabit and will pass on to future generations. And perhaps this is the real meaning of being inheritors. It's not just about receiving a legacy, it's about what we do with it, how we steward it, what we pass on to whatever comes after us. The mammals inherited a devastated world and, over millions of years, built it into the diverse, complex ecosystems we know today. We've inherited those ecosystems. The question is what we'll make of them, what future organisms will inherit from us. The dinosaurs couldn't prevent their extinction, but their story teaches us about the consequences of catastrophic environmental change. They were exquisitely adapted to their world, successful beyond measure, and yet vulnerable to changes they couldn't predict or control. We're similarly adapted to our current world, successful in our own way, but potentially vulnerable to changes we can predict and possibly control. The difference is knowledge. We know about asteroid impacts, we know about climate change, we know about extinction rates and ecosystem collapse and environmental tipping points. The dinosaurs didn't know and couldn't have known. We do, and that knowledge creates responsibility, the obligation to use what we understand to make wise choices, to be good ancestors to whatever future generations or species come after us. And this responsibility brings us to consider what the future might hold, what patterns we can see in the long history of life on Earth, and what they suggest about what comes next. Looking backward through deep time, we can see patterns in how life has evolved, how it's responded to catastrophes, how it's changed and persisted over billions of years. These patterns might tell us something about the future, about what we can expect, about how the story might continue. One clear pattern is that life is remarkably persistent. Despite 5 major mass extinctions and numerous smaller ones, despite asteroid impacts and supervolcano eruptions and extreme climate changes, life has continued. It's been stressed, reduced, pushed to the brink, but never eliminated. The biosphere as a whole has proven more resilient than any individual species or ecosystem. This suggests that life, in some form, will likely continue into the future, regardless of what challenges emerge. Another pattern is increasing complexity over time. The earliest life was simple, single-celled organisms. Over billions of years, life evolved multicellular forms, then complex organisms, then organisms with specialized tissues and organs, then nervous systems and brains, then consciousness and intelligence. This trend toward increasing complexity isn't universal. Many organisms remain simple because simplicity works for them, but the maximum complexity has increased over Earth's history. This pattern might continue. Perhaps intelligence will continue to evolve, perhaps in new forms or new lineages. Perhaps consciousness will become more common among Earth's organisms. Perhaps entirely new levels of organization will emerge, ways of being alive that we currently can't imagine. The future might be as different from the present as the present is from the Cretaceous, filled with organisms and ecosystems that would seem alien to us. A third pattern is that catastrophes, while devastating in the short term, can be creative in the long term. Each major extinction has been followed by radiation, diversification, the evolution of new forms to fill empty ecological space. The Permian extinction, the worst of the 5 major extinctions, was followed by the radiation of archosaurs that eventually produced dinosaurs. The Cretaceous-Paleogene extinction was followed by the mammalian radiation that eventually produced humans. If this pattern continues, and there's no particular reason to think it won't, then future catastrophes, if they occur, will likely be followed by new radiations. New evolutionary innovations, new forms of life we can't predict. The biosphere will recover, as it always has, and the recovery will produce something genuinely new. But there's a new element in the pattern now: human influence. For the first time in Earth's history, a single species has the ability to significantly alter global ecosystems, to cause extinctions on a massive scale, to change the climate, to modify the environment in ways that affect organisms across the entire planet. This is unprecedented. No previous species has had this kind of power. This could disrupt the patterns. If humans cause a mass extinction on the scale of the Chicxulub event, the recovery might follow different trajectories than previous recoveries because the cause is different, internal to the biosphere rather than external. If we alter the climate dramatically, we might create conditions that haven't existed for millions of years, forcing life to adapt to a world it hasn't experienced in its recent evolutionary history. But there's also the possibility that human intelligence and technology could stabilize the biosphere in ways that natural processes alone cannot. We could, in theory, prevent asteroid impacts, moderate climate change, protect biodiversity, create conditions for long-term ecosystem stability. We could become conscious stewards of the biosphere rather than unconscious participants in its destruction. This is speculative, of course. We don't know what will happen. The future is genuinely uncertain, open to multiple possibilities depending on choices we haven't yet made. But the patterns from the past give us some framework for thinking about what might come, what's likely, what's possible. One likely outcome is continued change. The current configuration of ecosystems, the current distribution of species, the current climate, all of these are temporary. They'll change, either gradually through normal evolutionary and geological processes, or rapidly through catastrophes, either natural or human-caused. The world a million years from now will be different from the world today, just as today's world is different from the Cretaceous. Another likely outcome is survival of life in some form. Even if humans cause significant extinctions, even if we alter the climate dramatically, even if we disrupt ecosystems globally, life will probably persist. Some organisms will survive. Evolution will continue. The biosphere will adapt to whatever conditions exist, as it has adapted to every previous change in Earth's history. A possible outcome, though less certain, is the emergence of new forms of intelligence. Humans might persist and continue to evolve, biologically or culturally or through technology. Other lineages might evolve intelligence as primates did, creating new conscious beings with their own perspectives on existence. Or intelligence might remain rare, a brief experiment in Earth's history, interesting but not fundamental to the biosphere's functioning. The pattern that seems most reliable, looking backward through deep time, is continuation. Life continues, change continues, evolution continues, the specific forms change, the dominant groups change, the ecosystems change, but the process itself, the ongoing flow of life through time, persists through everything. And this persistence, this fundamental resilience of life as a process rather than as specific forms, suggests that the story will continue, that there will be a future, that what comes after us will be shaped by what we do, but not determined entirely by it. And this understanding of continuation brings us close to the end of our journey, to a place where we can begin to find peace in what we've explored and meaning in the long view of time. We're approaching the end of our journey now, and it's time to gather the threads, to synthesize what we've explored, to find in this story of ancient catastrophe something that brings peace rather than anxiety, comfort rather than dread. Because the story of the Chicxulub impact, properly understood, is not fundamentally a story about death and destruction. It's a story about transformation, about how life continues through and past catastrophes, about the resilience of existence itself. The dinosaurs are gone, but their story isn't a tragedy in the classical sense. They existed. They lived for more than 160 million years. They filled the earth with countless forms, from the tiny to the massive, from the swift to the lumbering, from the predators to the herbivores. They experienced existence in ways we can only imagine. They were subjects, not just objects, alive in the fullest sense, and then they ended, and something else began. This is the pattern of existence, not just for dinosaurs, but for everything. Things arise, exist for their time, and then pass, making way for new things. This isn't pessimistic. It's just accurate, a description of how time works, how change operates, how the universe functions. And there's peace in accepting this, in not fighting against the fundamental impermanence of all things, but instead recognizing it as the mechanism by which existence continues. Imagine if the dinosaurs hadn't gone extinct. The world would be very different, perhaps unrecognizably so. Mammals would likely still be small and nocturnal. Humans would never have evolved. The ecosystems we know, the animals we live alongside, the very structure of life on Earth, all of this depends on the dinosaurs ending. Their extinction was the condition for our existence, the event that made the modern world possible. This doesn't mean we should celebrate extinctions or welcome catastrophes. Individual deaths matter. Species have inherent value. Suffering is real and should be minimized where possible. But it does mean we can have perspective, can recognize that endings, while difficult, are also necessary for beginnings, that transformation requires letting go of what was to make space for what will be. The Chicxulub impact teaches us that even the most devastating changes are survivable for life as a whole. 66 million years ago, the world experienced one of the worst catastrophes in its history. The skies darkened, the temperature plummeted, most species died, and yet, here we are. Life recovered, ecosystems rebuilt, new forms evolved. The catastrophe, while real and devastating in the moment, was temporary in the larger flow of time. This pattern repeats throughout Earth's history. Every major extinction is followed by recovery and radiation. Every catastrophe, given enough time, becomes just another chapter in life's long story, terrible in the moment but ultimately survivable, ultimately part of the larger pattern of continuation. And this pattern gives us reason for hope, not naive optimism that ignores real problems, but grounded hope based on billions of years of evidence that life persists, adapts, continues. For us, living in the present, facing our own challenges and uncertainties, this long view can be calming. The problems we face, the environmental changes, the extinction rates, the climate disruption, all of these are serious and deserve our attention and effort. But they're also temporary, part of a particular moment in Earth's history, solvable in principle, survivable in the long run. Life has faced worse and continued. This doesn't absolve us of responsibility. We should still work to prevent unnecessary extinctions, to stabilize the climate, to protect ecosystems. But it means we can do this work without despair, without believing that everything is hopeless, without imagining that current challenges represent the end of everything. They don't. They represent a difficult moment, a time of transition, a period of change. But change is what life does. It's been changing for billions of years and will continue to change for billions more. There's a kind of peace in accepting our role in this larger story, in recognizing that we're participants in something much larger and longer than our individual lives or even our species' existence. We're part of the continuation of a life on Earth, the current expression of a process that began billions of years ago and will continue long after we're gone. Our actions matter in the immediate sense to us, to other species alive now, to the specific moment we inhabit. But in the long view, we're just one chapter in a much longer book, important to the characters in that chapter, but ultimately part of a larger narrative that continues past us. The dinosaurs didn't know they were temporary. They couldn't conceive of their own extinction. They simply lived as fully as they could for as long as they existed. And perhaps this is the right approach for us too, to live fully in the present, to care for what exists now, to make wise choices based on what we know, while also accepting that our time, like all times, is temporary, part of a flow that will continue in ways we can't predict or control. The Chicxulub impact happened 66 million years ago. The dinosaurs died. The world changed, life continued, and here we are, the inheritors of that ancient catastrophe, alive in a world shaped by that event, contemplating it on a quiet night, finding in its story something that speaks to our own situation, our own challenges, our own place in the long arc of existence. And this contemplation, this reflection on deep time and transformation, brings us to the final moments of our journey, where we can rest in what we've learned and find peace in the understanding that comes from looking backward through time and forward into an uncertain but continuing future. Let's rest here for a moment in what some philosophers and thinkers call the long now, the sense of time that extends backward through history and forward into the future, encompassing both what was and what might be, holding past and future in awareness simultaneously with the present moment. This is the final insight, the last contemplation, the place where all the threads of our journey come together in understanding that's both intellectual and felt. The dinosaurs existed in their own long now, though they couldn't consciously perceive it as such. Their present was shaped by millions of years of evolution that came before them. Their existence shaped what would come after, though they couldn't know it. They were links in a chain stretching from the deep past into the distant future, carrying forward the legacy of ancient organisms and passing it on to descendants they would never meet. We exist in the same kind of long now. Our present is shaped by everything that came before. From the formation of Earth to the first life, to the extinction of the dinosaurs, to the evolution of primates, to the development of human civilization, we carry in our bodies, in our genes, in the very structure of our cells, the legacy of billions of years of evolution. We are ancient and modern simultaneously, the product of deep time existing in a single moment. And what we do now shapes what comes after. Just as what the dinosaurs did in their time shaped the conditions we inherited. Our choices matter not just for ourselves, but for the future organisms that will inherit the world we leave behind. We're writing a chapter in Earth's long story, and that chapter will be read by whatever comes after us, whether that's future humans or entirely new forms of life we can't imagine. This perspective, this awareness of existing in the long now, can change how we think about our actions and choices. Things that seem urgent in the moment, the immediate pressures and concerns, remain important but are also contextualized by the awareness that they're part of a much longer flow. The question becomes not just what do we want right now, but what kind of chapter do we want to write? What legacy do we want to leave? How do we want to be remembered in the long story of life on Earth? The dinosaurs are remembered as successful, dominant for an extraordinary length of time, diverse and remarkable. They're also remembered for their extinction, for being the group that ended when the world changed too rapidly for them to adapt. Both of these things are true. They were both incredibly successful and ultimately unable to prevent their own end. This is not a contradiction. It's the pattern of existence, the way things work in a universe where nothing is permanent. How will we be remembered? As the species that developed consciousness and intelligence and technology, as the species that understood enough to prevent its own extinction and chose to do so, or as the species that had the knowledge to survive but failed to use it wisely? The answer isn't determined yet. We're writing it now, in the choices we make, the actions we take, the world we create or destroy. But regardless of how our specific chapter ends, the story will continue. This is perhaps the deepest piece available in contemplating deep time and the long now. We're not responsible for writing the entire story, just our chapter. We're not responsible for ensuring life continues forever, just for stewarding it during our time. We're not responsible for preventing all future catastrophes, just for dealing wisely with the ones we can influence. The Earth has survived far worse than anything humans have done or likely will do. It survived the Permian extinction, which eliminated 96% of marine species. It survived the Chicxulub impact. It survived being nearly completely frozen, nearly completely molten, nearly completely without oxygen. Life has persisted through all of this. The biosphere is resilient on timescales of millions of years, capable of recovering from catastrophes that seem world-ending in the moment. This resilience doesn't excuse carelessness or justify destruction, but it does provide perspective, the understanding that our moment however important to us, is one moment in a very long story. We matter, our choices matter, the future we create matters. But we're also part of something much larger than ourselves, participating in a flow of existence that extends far beyond our individual or even species existence. The dinosaurs teach us this through their absence. They're gone, completely gone, except for their bird descendants and the fossils they left behind. Their entire reign, more than 160 million years of dominance, is now just a memory preserved in rock, studied by organisms that evolved long after they vanished. And yet their story matters. They existed. They shaped their world. They left a legacy that continues to influence the present. Our story will be similar. We exist now, shaping our world, making choices that will echo into the future. Eventually we too will be gone, either extinct or evolved into something so different that we wouldn't recognize our descendants. And future organisms, whatever they are, will study our fossils, try to understand how we lived, what we did, why we vanished or transformed. They'll fit us into the long story of life on Earth, another chapter, important for what it tells about evolution and existence, but ultimately just one chapter among many. And there's peace in this, in accepting our place in the long now, in recognizing that we're part of something larger and longer than ourselves. It removes the pressure of thinking everything depends on us, the anxiety that our failure would end everything. It won't. Life will continue. The story will go on. Our chapter matters, but it's not the whole book. And this understanding allows us to act with both responsibility for our moment and peace about the larger flow of time. The long now stretches backward through billions of years and forward through billions more. We exist in a brief moment within that vast expanse, aware of it in a way that no previous organism has been, capable of understanding our place in deep time and our connection to everything that came before and everything that will come after. This awareness is a gift, a perspective that allows us to see our lives and our time in context, to act with both urgency and equanimity, to care deeply about the present while accepting the flow of time that carries us all forward into an unknown but continuing future. And with this understanding we can finally rest, can let go of the need to know everything or control everything, and simply be here, now, in this moment, part of the long story of life on Earth. We've travelled together through 66 million years tonight, from the final ordinary morning of the Cretaceous period through the fire and darkness of the impact and its aftermath, through the long recovery and the patterns of deep time, arriving here, now, in the quiet of this moment. Thank you for staying with this story, for lending me your attention for these 2.5 hours, for letting these ancient events and distant catastrophes find a place in your thoughts on this particular evening. From a shallow tropical sea where the sky caught fire to the darkness that followed, from the extinction of the dinosaurs to the rise of the mammals, from the science of impacts and recovery to the philosophy of change and continuation, we've covered a remarkable span of time and thought. We began with a question implicit in our title. What really happened in those final hours before extinction? And the answer, as honestly as I can give it, is that the world ended and began again, simultaneously, catastrophically, ultimately survivably. If you enjoyed this slow drift through deep time, a like and subscribe helps reach others seeking the same peaceful way to end their day. I'd love to hear your thoughts in the comments, what resonated with you, what questions you still carry, what peace you found in contemplating timescales so vast that our worries dissolve into them. And to those who've been here before, who've joined me on previous journeys through space and time and ancient history, thank you. Your continued presence means more than you might realize. Wherever you are in the world right now, whatever has brought you to this quiet moment, I hope you're comfortable. I hope your breathing has slowed and deepened over these hours. I hope your body feels heavy and warm, ready for rest. I hope the concerns of the day have faded somewhat, made smaller by the perspective of deep time the understanding that everything changes and everything continues, that endings are also beginnings, that the story goes on. Look up at the night sky if you can, or imagine it if you can't. Those same stars look down on the last dinosaurs, witnessed the fire in the sky 66 million years ago, shone on the darkness that followed and the recovery that came after. They'll still be there tomorrow night and the night after, mostly unchanged on timescales of human existence, slowly evolving on timescales of stellar time. The universe is vast, ancient, continuing, and we're part of it, brief and beautiful and temporary, like the dinosaurs were, like everything that has ever existed or will exist. The Chicxulub impact teaches us that catastrophes happen, that the world can change in an afternoon, that even the most successful organisms can end suddenly and completely. But it also teaches us that life continues, that recovery is possible, that transformation is how existence works. The endings make space for beginnings. Both of these truths exist together, not cancelling each other out but complementing each other, giving us the full picture of how life persists through time. Sleep well tonight. Dream, if you dream, of ancient worlds and deep time, of forests that no longer exist and animals that vanished millions of years ago, of the long arc of existence that connects past to present to future. Dream of transformation and continuation, of endings and beginnings, of the resilience of life and the peace that comes from accepting impermanence. And when you wake tomorrow, carry with you the understanding that you're part of something larger and longer than yourself, a participant in the ongoing story of life on Earth, writing your small chapter in a book that began billions of years ago and will continue long after you're gone. Good night. Rest well. And thank you, truly, for spending these hours exploring deep time with me, for finding in the story of ancient extinction something that speaks to the present moment, for being here, now, in this shared contemplation of what was, what is, and what might yet be.